Hello there, and welcome to Science for Sleep, where curiosity slows down for the evening and the universe becomes just a little softer around the edges. Tonight, we're travelling very far from home, far beyond the rocky planets, beyond the gas giants, beyond the familiar orbits we usually picture when we think about the solar system. Out there, in the cold darkness past Neptune, lies a region so enormous and so strangely empty that even now, after decades of exploration, we still don't fully understand where it ends. And that quiet frontier is called the Kuiper Belt. Now, if you've ever seen a diagram of the solar system in a classroom or a book, the Kuiper Belt might have looked rather tidy. A neat little ring of icy objects sitting politely beyond Pluto, almost like the cosmic version of a storage shelf. But the real thing is far stranger than that. It's wider than most people imagine, darker than almost anywhere humans have ever studied, and filled with frozen worlds drifting slowly around the sun in near silence. Some of them are larger than entire countries. Some may once have been planets, and some have been orbiting out there unchanged for more than 4 billion years, quietly circling the sun since the earliest days of the solar system itself. So tonight, we're going to wander through this distant region together. We'll explore how big the Kuiper Belt really is, why scientists spent so long searching for it, what lives inside it, and why this frozen band of debris may hold clues to how the entire solar system came to exist in the first place. But before we begin drifting out toward the edge of sunlight, I'd love to know something simple. Where are you listening from tonight? And what time is it in your little corner of the world right now? Perhaps it's late evening. Perhaps it's raining outside. Maybe you're already half wrapped in blankets, wondering how a region full of invisible ice rocks somehow became tonight's bedtime destination. It is admittedly a slightly unusual travel itinerary. Still, if you find these quiet journeys soothing or comforting after a long day, I'd be very grateful if you liked the video and maybe subscribed as well. It helps this small, sleepy corner of science continue drifting through the algorithm instead of vanishing into the void like a forgotten probe somewhere beyond Neptune. And with that, let's slowly head outward. The solar system is much larger than most of us instinctively think it is. Our brains are not particularly good at understanding enormous distances. We're comfortable with kilometers and cities and maybe even continents. But space operates on scales so large that ordinary comparisons begin to fail very quickly. For example, light. The fastest thing in the universe takes a little over 8 minutes to travel from the Sun to Earth. That already sounds far. But Neptune, the outermost major planet, sits roughly 30 times farther from the Sun than Earth does. Sunlight reaching Neptune has already been travelling for more than 4 hours. And beyond Neptune is where things start becoming truly strange. Because many people grow up thinking Pluto marks the edge of the solar system, the lonely little world sitting at the outer boundary where everything simply stops. But Pluto is not the edge. In many ways, Pluto is actually the beginning of something much larger. Pluto lives inside the Kuiper Belt. That realization changed astronomy forever. Back in the early 20th century, Pluto was discovered almost by accident. Astronomers had been searching for what they believed was a hidden giant planet tugging on Neptune's orbit. Instead, in 1930, American astronomer Clyde Tombaugh found a tiny moving object far beyond Neptune. At first, Pluto seemed extraordinary, a mysterious distant planet sitting alone in the darkness. But over time, scientists began noticing something odd. Pluto was small, much smaller than expected. In fact, eventually astronomers realized Pluto wasn't even close to Earth's size. It's actually smaller than Earth's moon. That raised an uncomfortable question. If Pluto was so tiny, why was it out there alone? Why would the solar system suddenly place one small frozen object far beyond Neptune and then simply stop? That question lingered for decades. Meanwhile, astronomers kept improving their telescopes. Better cameras appeared, digital imaging arrived, computers became powerful enough to compare huge sections of the night sky automatically, instead of relying on humans blinking back and forth between photographic plates for hours at a time. and eventually the outer darkness started revealing more objects. First one, then another, then dozens, then hundreds. Suddenly Pluto no longer looked unique at all. It looked like part of a crowd. That crowd became known as the Kuiper Belt, named after astronomer Gerard Kuiper, although interestingly Kuiper himself did not exactly predict the belt as we understand it today. Science history can be slightly messy that way. Sometimes people become attached to discoveries they only partially anticipated, a bit like accidentally inventing a recipe while trying to clean out your refrigerator. The Kuiper Belt turned out to be an enormous region filled with icy remnants from the solar system's formation. Objects made of frozen water, methane, ammonia, and ancient rock, all orbiting far beyond Neptune where temperatures are so cold that even nitrogen can freeze solid. And once astronomers realized how many objects existed out there, Pluto's status suddenly became complicated. Because if Pluto was a planet, then what about all these other worlds? Some were nearly as large, some had moons, some followed strange tilted orbits. One object named Eris even appeared slightly more massive than Pluto itself. Astronomy had a problem. Either the solar system suddenly contained dozens of planets, or the definition of planet needed to change. And eventually, of course, Pluto was reclassified as a dwarf planet in 2006 by the International Astronomical Union. That decision upset many people, partly because humans tend to become emotionally attached to categories we learned as children. Also because Pluto has a certain underdog quality. Small, distant, slightly lonely. The solar system's forgotten little ice world. Except Pluto was never lonely at all. It was surrounded by an entire hidden region we had barely begun to notice, and that region is astonishingly large. When most people picture asteroid belts, they imagine something crowded, perhaps a chaotic field of tumbling rocks packed closely together, like scenes from science fiction films where spaceships weave dramatically between incoming boulders every few seconds. The real Kuiper Belt is nothing like that. In fact, if you were standing on Pluto, the night sky would still mostly look empty. The objects out there are separated by immense distances. Even though the Kuiper Belt contains countless icy bodies, space itself is simply too vast for them to cluster tightly together. Individual objects may be millions of kilometers apart. That's one of the strange things about the universe. It can be both crowded and empty at the same time. The Kuiper Belt begins roughly around Neptune's orbit, at about 30 astronomical units from the Sun. An astronomical unit, or a U, is simply the average distance between Earth and the Sun, about 150 million kilometers. So right away we're already talking about enormous scales. The Kuiper Belt stretches outward from around 30 astronomical units to roughly 50 astronomical units, though some scattered objects travel much farther than that. Pluto itself orbits at an average distance of about 39 astronomical units. Just reaching Pluto took NASA's NASA spacecraft New Horizons nearly 9.5 years travelling at incredible speed. And even then, New Horizons was moving so quickly that it passed Pluto in only a matter of hours before continuing deeper into the darkness. Imagine taking nearly a decade to arrive somewhere, and then flying past before lunch. That is the scale we're dealing with. Now, here's where things become even more difficult for the human mind to process. The Kuiper Belt is not merely wide, it also contains three-dimensional structure. Some objects orbit in relatively flat paths close to the plane of the solar system. Others tilt dramatically upward or downward. Certain objects follow elongated orbits stretched into strange shapes by Neptune's gravity. Some may eventually get flung inward toward the Sun, becoming comets visible from Earth. Others drift so far outward they enter the even larger and more mysterious scattered disk region. And farther still, perhaps unimaginably far away, lies the hypothetical Oort cloud, which may surround the solar system like a gigantic frozen shell extending nearly halfway to the nearest stars, but that is another sleepy journey entirely. For now, we remain within the Kuiper Belt itself, this cold outer zone where sunlight grows weak and time seems almost suspended. temperatures there can drop below minus 220 degrees Celsius. At those temperatures, the sun no longer resembles the bright blazing star we know from Earth. Instead, it would appear more like an extremely brilliant point of light in a permanently dark sky. Still bright enough to hurt your eyes, but distant, remote, almost detached. And despite all that distance, the Kuiper Belt matters enormously. Because these frozen objects are ancient. Unlike Earth, which has been reshaped constantly by oceans, volcanoes, weather and tectonic activity, many Kuiper Belt objects have remained relatively unchanged since the solar system formed around 4.6 billion years ago. They are time capsules, frozen leftovers from the original cloud of gas and dust that created the planets. That means studying them is a bit like opening a cosmic freezer and discovering ingredients left over from the solar system's earliest recipe. Not necessarily appetizing ingredients, mostly ice and rock, but scientifically very exciting. Astronomers believe the giant planets, particularly Jupiter and Neptune, dramatically influenced the Kuiper Belt long ago. Early in solar system history, the giant planets may have migrated from different original positions. As they moved, their gravity scattered enormous numbers of icy bodies outward. Some were ejected from the solar system entirely. Some crashed into planets. Some became moons, and many ended up trapped in the distant outer regions beyond Neptune. That means the Kuiper Belt is not just debris, it's evidence, a surviving record of ancient planetary chaos, which is quite comforting in a strange way. Even our solar system appears to have gone through an extremely disorganized phase before settling down. Admittedly, its version of settling down still involves giant storms, radioactive worlds, frozen methane landscapes, and occasional comets flying inward at terrifying speeds. But by cosmic standards, things are relatively calm these days. Although the Kuiper Belt remained hypothetical for much of the 20th century, astronomers slowly gathered more proof that something large existed beyond Neptune. Then came 1992. That year, astronomers David Jewett and Jane Liu discovered an object officially designated 1992 QB1. Not the catchiest name astronomy has ever produced. Space scientists are brilliant at orbital mechanics, but occasionally less gifted at branding. Still, the discovery mattered enormously, because it confirmed Pluto was not alone. There truly was an entire population of objects beyond Neptune, and once scientists knew where to look, discoveries accelerated rapidly. Today, astronomers have identified thousands of Kuiper Belt objects, often shortened to KBOs. Many are tiny, some are gigantic, a few rival Pluto in size. There may actually be hundreds of thousands of objects larger than 100 kilometers across hiding out there, along with millions of smaller ones. And we've only discovered a fraction of them. That's one of the most astonishing parts. Even now, despite modern telescopes and space probes, much of the Kuiper Belt remains unknown simply because it is so dark and distant. Many objects reflect very little sunlight. They move slowly across the sky. Detecting them requires patience, sensitive instruments, and years of observation. In a sense, astronomers searching the Kuiper Belt are doing something remarkably similar to ancient sailors crossing dark oceans. They are mapping faint distant territory, one small discovery at a time. And sometimes the discoveries become very strange indeed. Some Kuiper Belt objects rotate chaotically. Some appear reddish due to radiation altering their frozen surfaces over billions of years. Some have moons. Some may contain subsurface oceans beneath layers of ice. And a few objects follow bizarre clustered orbits that have led scientists to speculate about the existence of another hidden world much farther away, often nicknamed Planet 9. Now, whether Planet 9 actually exists remains uncertain. Astronomers continue searching. It may turn out to be real, or the strange orbital patterns may have another explanation entirely. Still, the idea itself reveals something important. We do not fully know what exists in the outer solar system. That realization is oddly humbling. For centuries, humans believed the solar system ended shortly after Saturn. Then Uranus appeared, then Neptune, then Pluto, then the Kuiper Belt itself. Each time we looked farther outward, the universe quietly revealed that reality was larger than expected. And perhaps it still is. Out beyond Neptune, there are worlds no human eyes will ever see directly without machines. Tiny frozen bodies orbiting in darkness for billions of years, while life evolved on Earth completely unaware of them. Dinosaurs came and went, mountains rose and eroded, entire species appeared and vanished. Meanwhile, these distant icy objects simply kept circling the sun in silence, slowly, patiently, orbit after orbit after orbit. Long before astronomers confirmed the existence of the Kuiper Belt, there was already a growing suspicion that something unusual waited beyond Neptune. The outer solar system did not behave quite as neatly as scientists expected. Tiny irregularities appeared in calculations. Strange objects drifted at impossible distances, and perhaps most importantly, Pluto itself refused to fit comfortably into the picture astronomers had originally imagined. That was the first real clue, not an explosion of discovery, not a dramatic telescope image, just a lingering scientific discomfort, the kind that quietly sits in the background for decades while researchers continue asking the same stubborn question. Something out there does not make sense. Back in the 19th century, astronomy was entering a remarkable period of precision. Telescopes improved steadily, mathematics became increasingly sophisticated, and scientists started realizing they could predict planetary motion with extraordinary accuracy. In fact, Neptune itself was discovered through mathematics before anyone actually saw it through a telescope. That remains one of the most impressive detective stories in science. Astronomers studying the orbit of Uranus noticed slight irregularities. Uranus did not move exactly as expected. It appeared to wobble slightly under the influence of some unseen gravitational force. Rather than dismissing the problem, scientists proposed an extraordinary idea. Maybe another planet existed farther out, pulling on Uranus with its gravity. And remarkably, they were correct. In 1846, astronomers finally observed Neptune almost exactly where calculations predicted it would be. It was a triumph for physics and astronomy alike. Suddenly, the solar system felt understandable, predictable, ordered, at least briefly. Because eventually astronomers began noticing additional irregularities involving Neptune itself. Tiny discrepancies, subtle gravitational puzzles. Once again, speculation started growing about another hidden planet lurking even farther outward in the darkness. This hypothetical world became known as Planet X. Now, there is something very human about this pattern. Whenever we discover one boundary, we immediately wonder if another lies beyond it. Sailors crossed oceans wondering what waited past the horizon. Explorers climbed mountains only to find larger mountain ranges behind them. Astronomers, meanwhile, kept staring farther into space, asking, what comes next? And so, the search began. One of the most important figures in this story was Percival Lowell, an astronomer deeply fascinated by the idea of unseen planets. Lowell became convinced that Planet X existed beyond Neptune and spent years searching for it at the Lowell Observatory in Arizona. Lowell was an unusual character even by astronomer standards, which is saying quite a lot. He strongly believed intelligent canals existed on Mars, a conclusion that turned out to be incorrect but certainly memorable. Still, despite some questionable Martian enthusiasm, Lowell was serious about the hunt for Planet X. The challenge, however, was enormous. Objects beyond Neptune move very slowly across the sky because they are so distant. Imagine trying to notice the movement of a tiny dim speck over several nights, while surrounded by millions of stars that remain fixed in place. The process required painstaking comparison of photographic plates taken days apart. Astronomers used devices called blink comparators, machines that rapidly switched between two photographs of the same section of sky. Stars stayed stationary, but moving objects appeared to jump back and forth. It was astronomy's version of finding a cosmic typo. After Lowell died in 1916, the search continued. Years passed without success. Then eventually in 1930, a young astronomer named Clyde Tombaugh identified a faint moving object beyond Neptune. That object was Pluto. The discovery generated enormous excitement. At last, it seemed Planet X had been found. Except almost immediately, problems appeared. Pluto was too small. At first, astronomers assumed Pluto must be fairly large, perhaps Earth-sized or bigger. But as observations improved over the following decades, Pluto's estimated mass kept shrinking. Eventually, scientists realized Pluto was tiny compared to the giant planets, extremely tiny. Its diameter is only about 2,377 kilometers, smaller than Earth's moon, smaller even than several moons orbiting the giant planets. That created a major issue. How could such a small object significantly influence Neptune's orbit? The answer, eventually, turned out to be rather awkward. It couldn't. Later calculations reveal the supposed irregularities in Neptune's orbit were largely the result of inaccurate measurements of Neptune's mass. Once scientists corrected those values using better observational data from spacecraft, the need for Planet X mostly vanished. In other words, Pluto had been discovered during a search for something else entirely. Astronomy occasionally works that way. You spend years looking for one mystery and accidentally uncover a different one instead. Still, Pluto itself remained fascinating. Here was a frozen world orbiting far beyond Neptune in deep darkness. Unlike the major planets, Pluto followed a highly tilted and elongated orbit. Sometimes it actually travelled closer to the Sun than Neptune itself. It looked unusual, almost out of place. For decades, astronomers debated what Pluto truly was. Some suspected it might belong to a larger population of distant icy objects. Others wondered if it had once been a moon of Neptune somehow ejected into an independent orbit. The outer solar system remained deeply mysterious, because observing distant objects was incredibly difficult at the time. Even Pluto appeared only as a blurry point of light through most telescopes. No surface details were visible, no neighbouring objects could easily be seen, and yet a few scientists had already started proposing a bold possibility. Maybe Pluto was not alone at all. One of the earliest astronomers to seriously suggest this idea was Kenneth Edgeworth during the 1940s. Edgeworth proposed that the outer solar system might contain many small icy bodies left over from planetary formation. According to his reasoning, material far beyond Neptune would have been too spread out to combine into large planets successfully. Instead, countless smaller objects may have remained scattered throughout the region. Then later, in 1951, astronomer Gerard Kuiper discussed a somewhat similar concept involving icy remnants beyond Neptune, although his exact model differed from what we now call the Kuiper Belt. Interestingly, Kuiper himself actually believed such objects may no longer exist in large numbers because he thought the region would have dispersed over time. Science history is wonderfully untidy sometimes. The Kuiper Belt ended up named after someone who did not fully predict its modern form, while Edgeworth, who contributed enormously to the idea, is often less remembered outside astronomy circles. In some parts of Europe, scientists even refer to the region as the Edgeworth-Kuiper Belt instead. Regardless of naming debates, the central idea was beginning to take shape. The outer solar system might contain a huge population of icy leftovers, but proving that idea required better technology, and technology was finally starting to catch up. Throughout the mid-20th century, telescopes improved steadily. Electronic detectors replaced photographic plates. Computers transformed astronomy by allowing researchers to analyze enormous amounts of data much more efficiently. Scientists could now search deeper into the darkness than ever before. At the same time, something else was becoming increasingly important: space exploration. Once humans started sending robotics, spacecraft outward, the solar system stopped being a collection of distant lights and became a physical place with real landscapes, weather systems, moons, and geological complexity. The NASA missions of the 1970s and 1980s transformed planetary science completely. Voyager 1 and Voyager 2 revealed astonishing details about the giant planets and their moons. Enormous storms, active volcanoes, frozen oceans, ring systems, magnetic fields, and then Voyager 2 reached Neptune in 1989. Until that flyby, Neptune had remained little more than a distant blue disk through telescopes. Suddenly, humanity saw it up close. A cold, turbulent world with supersonic winds and strange moons drifting through deep darkness. One moon in particular caught scientists' attention: Triton. Triton was bizarre. It orbited Neptune backward compared to the planet's rotation, suggesting it had probably not formed alongside Neptune originally. Instead, astronomers suspected Triton might actually be a captured object from beyond Neptune, possibly a former Kuiper Belt object. That realization hinted again that an enormous unseen population of icy worlds might exist farther outward. Meanwhile, comet research provided additional clues. Certain comets called short-period comets orbit the Sun relatively quickly, returning every few decades or centuries. Scientists needed to explain where these comets came from. The Oort cloud had already been proposed as the source of long-period comets, arriving from extremely distant regions. But short-period comets followed different orbital patterns. Many appeared linked to the plane of the solar system itself. Astronomers increasingly suspected they originated from a nearer reservoir beyond Neptune. Again and again, the clues kept pointing outward. Small icy bodies, frozen remnants, a hidden region beyond Neptune feeding comets inward. Still, no direct evidence existed yet. Then came one of the most important discoveries in modern planetary astronomy. In 1992, astronomers David Jewett and Jane Liu identified a faint object orbiting beyond Neptune called 1992 QB1. The name sounds less like a distant world and more like a rejected password suggestion. Nevertheless, it changed astronomy forever. This object became the first confirmed Kuiper Belt object discovered after Pluto and its moon Charon. At last, direct evidence existed. Pluto was not isolated. The outer solar system truly contained additional worlds, and once astronomers found one object, they quickly started finding more. That's often how discovery works in astronomy. The hardest object to find is the first one because scientists do not yet know exactly what they are looking for. Once patterns emerge, detection becomes easier. Soon dozens of Kuiper Belt objects appeared, then hundreds, then thousands. The picture of the solar system suddenly expanded dramatically. What had once seemed like empty space beyond Neptune was actually an enormous region filled with ancient icy bodies. And Pluto no longer looked special. That realization carried enormous consequences. For decades, children learned the solar system contained 9 planets, with Pluto occupying the outermost position, like a lonely frozen sentinel at the edge of the Sun's domain. But now astronomers faced an uncomfortable possibility. If Pluto counted as a planet, perhaps many newly discovered Kuiper Belt objects should also count, especially because some were surprisingly large. In 2002, astronomers discovered Quaoar, then Sedna, then Haumea, then Makemake, and finally in 2005 astronomers identified Eris, an object slightly more massive than Pluto. At that point, astronomy could no longer avoid the debate. Either the solar system would suddenly contain many additional planets, or Pluto's classification needed reconsideration. Eventually, as we know, Pluto became categorized as a dwarf planet in 2006. That decision triggered surprisingly emotional reactions worldwide. People protested, children wrote letters, teachers complained, some scientists disagreed openly, which is honestly rather charming when you think about it. Humanity became emotionally invested in a tiny frozen world, billions of kilometers away. Still, scientifically, the reclassification reflected a deeper truth. Pluto belonged to a much larger population. It was not the final planet standing alone at the edge of the solar system. It was one member of a vast hidden frontier we had only recently begun to understand. And the more astronomers studied the Kuiper Belt, the stranger it became. Some objects travelled in stable, resonant orbits controlled by Neptune's gravity. Pluto itself belongs to this category. For every 3 Neptune orbits, Pluto completes exactly 2. This gravitational relationship prevents collisions despite their overlapping paths. The universe occasionally displays astonishing mathematical neatness amid overwhelming chaos. Other Kuiper Belt objects followed wildly tilted trajectories. Some appeared reddish, from billions of years of radiation exposure. Others spun rapidly or possessed moons of their own, and the region itself turned out to be enormous. The Kuiper Belt extends across billions of kilometers. Yet despite containing huge numbers of objects, it remains incredibly sparse. If you travelled through it in a spacecraft, you would probably see almost nothing most of the time. No crowded asteroid field, no endless barrage of icy rocks, mostly darkness, cold sunlight, and scattered frozen worlds separated by immense distances. That combination of emptiness and enormity is difficult for the human mind to absorb properly. We instinctively imagine collections of objects as crowded because that is how collections behave on Earth. Forests are dense, cities are packed, beaches fill with people. But space does not work that way. Even the busiest regions of the solar system are mostly empty vacuum, and the Kuiper Belt sits so far from the sun that sunlight itself begins feeling thin and weak. Out there, daytime would resemble permanent twilight compared to Earth. Yet despite the distance, those frozen objects matter profoundly because they preserve clues from the earliest history of the solar system. They are ancient survivors, time capsules orbiting quietly beyond Neptune, and what began as a few faint clues gradually transformed into one of the biggest revisions in our understanding of the solar system ever made. For a long time, Pluto seemed completely alone. That loneliness shaped the way generations of people imagined the outer solar system. Beyond Neptune sat one tiny frozen planet, drifting through darkness at the edge of everything familiar. Small, cold, distant, almost forgotten. It had a certain personality because of that. The giant planets closer to the sun felt loud and dramatic. Jupiter had its giant storms and dozens of moons. Saturn carried those magnificent rings that looked almost decorative, as though the universe briefly decided to become artistic. Pluto, meanwhile, looked lonely, a little dim object orbiting quietly beyond all the others. But the strange thing is that Pluto only appeared isolated because humans lacked the tools to see its surroundings properly. Once astronomers improved their observations, they discovered Pluto lived inside an entire population of distant icy worlds, and suddenly Pluto's orbit stopped looking unique. Instead, it started looking like a clue. Now, Pluto's neighbourhood is one of the strangest regions in the solar system, because the rules there feel different. The neat, orderly arrangement people often imagine when thinking about planetary orbits begins to dissolve. Objects travel along tilted paths. Some orbits stretch into elongated ovals. Certain worlds move in synchronized gravitational rhythms controlled by Neptune. It is less like a neatly organized set of lanes, and more like an ancient frozen traffic pattern shaped by billions of years of gravity. To understand why Pluto's neighbourhood matters so much, it helps to start with Pluto itself, because Pluto is unusual in almost every possible way. First, its orbit is highly eccentric. That means it is not nearly as circular as the orbits of most planets. At its closest approach to the Sun, Pluto comes within about 30 astronomical units. At its farthest point, it travels nearly 50 astronomical units away. That is a huge difference. As a result, Pluto sometimes moves closer to the Sun than Neptune does. In fact, between 1979 and 1999, Pluto technically orbited inside Neptune's average distance from the Sun. That sounds slightly alarming at first. Two worlds crossing paths around the Sun feels like something that should eventually end very badly, and yet no collision can happen. Because Pluto and Neptune are locked into something called a resonance. This is one of those beautiful pieces of orbital mechanics that sounds complicated until you picture it properly. For every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. The timing works so perfectly that whenever Pluto crosses Neptune's orbital distance, Neptune itself is always somewhere else entirely. It's like 2 runners sharing part of a racetrack but always arriving at different times. The result is an incredibly stable gravitational dance that has lasted for billions of years, and Pluto is not alone in this pattern. Astronomers eventually discovered many other Kuiper Belt objects sharing similar orbital resonances with Neptune. Some follow the same 3:2 resonance as Pluto. These objects became known informally as Plutinos, meaning little Plutos, which sounds surprisingly adorable for ancient frozen worlds drifting through cosmic darkness. There are also objects trapped in other resonances. Some complete 1 orbit for every 2 Neptune orbits. Others follow more complicated gravitational relationships. This immediately told astronomers something important. Neptune's gravity had shaped the entire region. The outer solar system was not random debris scattered aimlessly. It contained structure, patterns, organization created by gravity over unimaginable spans of time. And the more scientists studied Pluto's neighborhood, the more complicated it became. The Kuiper Belt itself contains several overlapping populations of objects. Some travel in relatively calm, stable orbits close to the flat plane of the solar system. These are often called classical Kuiper Belt objects. Others belong to resonant populations controlled by Neptune. Then there are scattered objects travelling along highly stretched and tilted orbits, likely flung outward long ago through gravitational interactions with the giant planets. Pluto occupies a strange middle ground among all of this. It belongs to the resonant population, but it is also large enough to possess characteristics of a true world rather than merely a chunk of ice and rock, and Pluto really is a world. That became especially clear in 2015 when New Horizons finally arrived after travelling through space for nearly a decade. Before that mission, Pluto remained blurry even in our best telescopes. Scientists knew basic information about its orbit and size, but its surface was largely mysterious. Then suddenly humanity saw it properly for the first time, and Pluto turned out to be astonishing. Instead of a frozen dead rock, New Horizons revealed mountains made of water ice towering several kilometers high, vast plains of frozen nitrogen, strange polygon-shaped surface patterns, atmospheric hazes glowing blue in sunlight, evidence of glaciers slowly flowing across the landscape. It looked active, complex, alive in a geological sense. One region in particular captured global attention. A giant heart-shaped plain officially named Tombor Regio after Clyde Tombor. The universe occasionally produces moments that feel almost suspiciously poetic. A lonely, distant world humans barely understood for decades turns out to have a heart on its surface. Admittedly a heart made of frozen nitrogen ice at temperatures around minus 230 degrees Celsius, but still. The New Horizons mission changed Pluto from an abstract dot into a real place, and once Pluto became real, its neighbourhood started feeling real too. Because Pluto was clearly not some isolated anomaly. It belonged to a family of icy worlds sharing common origins. Some Kuiper Belt objects appear surprisingly similar to Pluto. Others are stranger still. Take Haumea, for example. Haumea is one of the weirdest objects in the outer solar system. It spins so rapidly that its shape has stretched into something resembling an elongated egg, or perhaps a slightly flattened rugby ball. A day on Haumea lasts only about 4 hours. That is extraordinarily fast for an object of its size. Its rapid rotation likely resulted from an ancient collision long ago. In fact, astronomers suspect Haumea may once have suffered a giant impact that blasted fragments into space, creating an entire family of related objects sharing similar compositions and orbital characteristics. Then there is Makemake, another large icy world with methane-covered surfaces giving it a reddish appearance. And farther outward lies Eris, whose discovery helped trigger Pluto's reclassification debate. Eris is slightly more massive than Pluto, although somewhat smaller in diameter. It travels along an extremely elongated orbit, carrying it far beyond the main Kuiper Belt. At its farthest point, Eris ventures over 90 astronomical units from the Sun. Imagine sunlight at that distance. On Earth, sunlight feels immediate and powerful. It warms skin instantly. It lights clouds and oceans and forests. But out near Eris, the Sun would appear almost star-like in the sky. Still bright, certainly, but emotionally distant somehow. The outer solar system exists in permanent deep cold, and yet these frozen worlds continue orbiting steadily for billions of years. What makes Pluto's neighbourhood especially fascinating is that scientists increasingly realise these objects preserve ancient history. Unlike Earth, where weather and tectonic activity constantly erase old geological evidence, Kuiper Belt objects remain relatively unchanged. They are survivors from the solar system's earliest era. Think about that for a moment. Before Earth had oceans, before the Moon fully formed, before life existed anywhere we know of, these icy bodies were already orbiting beyond Neptune. They witnessed the formation of planets themselves, and many still remain out there almost untouched. That ancient history helps explain why astronomers care so deeply about Pluto's neighbourhood. Studying these objects is not merely cataloguing distant ice balls, it is investigating the solar system's fossil record. The Kuiper Belt preserves clues about how planets formed, migrated, and interacted long ago. One leading theory describing this early chaos is called the Nice model, named after the French city where it was developed. According to this model, the giant planets originally formed in different positions than where we see them today. Over time, gravitational interactions caused them to migrate. Jupiter may have moved slightly inward, while Saturn, Uranus, and Neptune shifted outward. As Neptune moved outward, its gravity disturbed enormous numbers of icy bodies, scattering some deeper into space while trapping others into resonances. Pluto and many neighbouring objects may owe their current orbits to this ancient planetary migration. In other words, Pluto's strange neighbourhood may exist because the giant planets rearranged the outer solar system billions of years ago, which is slightly reassuring. Even the solar system appears to have gone through a chaotic restructuring phase. Now, another remarkable aspect of Pluto's neighbourhood involves moons, because many Kuiper Belt objects possess satellites. Pluto itself has 5 known moons. The largest, Charon, is enormous relative to Pluto's size. In fact, Charon is so large compared to Pluto that the two bodies actually orbit a point located outside Pluto itself. Some astronomers informally describe Pluto and Charon as a binary system rather than a traditional planet-moon arrangement. Charon transforms Pluto from a solitary object into something more complicated. The two worlds remain gravitationally locked, always showing the same faces to one another. Imagine standing on Pluto and seeing Charon hanging motionless in the sky forever, never rising or setting. That would feel deeply strange, especially because Charon itself is huge in Pluto's sky. Much larger in apparent size than Earth's moon appears from Earth. And farther across the Kuiper Belt, moons appear surprisingly common. This suggests collisions played an important role in shaping the outer solar system. Ancient impacts likely shattered some objects, formed moons around others, and altered rotational speeds dramatically. The Kuiper Belt may look calm today, but its early history was probably violent. Then again, much of the solar system's history appears surprisingly violent once you examine it closely. Even Earth suffered gigantic collisions early on. One likely created the Moon itself. The universe builds planets somewhat aggressively. Still, despite all this growing knowledge, Pluto's neighbourhood remains only partially explored. Most Kuiper Belt objects appear as tiny points of light even in powerful telescopes. Their surfaces remain mysterious, their exact compositions uncertain. Some may contain subsurface oceans beneath frozen crusts. Others may possess complex organic molecules altered by radiation over billions of years. There are likely countless undiscovered objects still waiting in the darkness, and that darkness is difficult to truly imagine. At Pluto's distance, sunlight is roughly 1,600 times weaker than on Earth. Daytime there would resemble a dim twilight compared to the brightness we experience here. Shadows would still exist, the sun would still cast light, but the entire environment would feel muted somehow, quiet, distant. That remoteness affects everything. A radio signal travelling at light speed still takes over 4 hours to cross the distance between Earth and Pluto when the two worlds are relatively close in their orbits. 4 hours. That means any communication with spacecraft out there happens with enormous delays. Engineers cannot control missions in real time. Everything must be planned carefully in advance. The outer solar system is so large that even light itself needs patience. And beyond Pluto's neighbourhood, the darkness continues even farther. Some objects like Sedna travel so far from the Sun that they may not fully belong to the Kuiper Belt at all. Sedna follows a bizarre elongated orbit requiring roughly 11,000 years to complete once. When Sedna reaches its farthest point, it travels more than 900 astronomical units away. At that distance, the Sun would appear merely as an exceptionally bright star. Sedna's strange orbit remains one of the great mysteries of the outer solar system. Some scientists suspect it was influenced long ago by passing stars during the Sun's early history inside its birth cluster. Others wonder whether an undiscovered giant planet may still lurk far beyond Neptune. Again and again, Pluto's neighbourhood keeps expanding into larger mysteries, and perhaps that is what makes it so captivating. Humans originally believed Pluto marked the end. Instead, Pluto became a doorway, a signpost pointing toward an enormous, unexplored frontier filled with frozen worlds, ancient debris, strange gravitational patterns, and unanswered questions stretching outward into the darkness beyond Neptune. By the time astronomers finally accepted that Pluto was not alone, another problem immediately appeared. What exactly was the Kuiper Belt? At first glance, the answer sounds simple. Most people hear the phrase and imagine something like an asteroid belt but farther away, a ring of icy rocks orbiting beyond Neptune. Technically, that is not entirely wrong, but it is also not remotely complete, because the Kuiper Belt is not a tidy ring of debris sitting neatly at the edge of the solar system. It is a huge, complicated, overlapping region shaped by gravity, migration, collisions, and billions of years of orbital chaos. Some parts are relatively stable, some are strangely empty, some contain objects travelling in synchronized patterns controlled by Neptune. Others contain worlds moving along wildly stretched trajectories, and perhaps most importantly, the Kuiper Belt is not merely a collection of leftovers, it is one of the oldest surviving structures in the solar system. In a way, it is less like a junkyard and more like a frozen archaeological site. Now, when astronomers talk about the Kuiper Belt, they are generally referring to a region beginning just beyond Neptune, roughly around 30 astronomical units from the Sun, and extending outward to about 50 astronomical units. That already sounds enormous because it is enormous. 1 astronomical unit, or AU, equals the average distance between Earth and the Sun, about 150 million kilometres, so the Kuiper Belt occupies a vast region billions of kilometres wide, and yet, strangely enough, it is still considered relatively close compared to what lies farther outward. The solar system is deeply unreasonable about scale. Humans tend to imagine edges as sharp boundaries, a coastline, a fence, a city limit sign. but space rarely behaves that way. Most structures in the universe fade gradually into other structures. The Kuiper Belt does not suddenly begin with a dramatic cosmic gate reading "frozen objects start here." Instead, it emerges gradually beyond Neptune, where increasing numbers of icy bodies begin appearing, and those icy bodies vary enormously in size. Some are tiny fragments only a few kilometers wide. Others are dwarf planets hundreds or even thousands of kilometers across. A few possess moons, some rotate rapidly, others tumble chaotically through space. Many are composed largely of ice mixed with rock and organic compounds, and when astronomers say ice, they do not just mean frozen water. Out there, substances we normally think of as gases on Earth become solid. Methane freezes, nitrogen freezes, carbon monoxide freezes. The outer solar system is cold enough to turn strange chemicals into permanent landscapes. Pluto itself contains nitrogen glaciers. Imagine explaining that casually to someone from the 1700s. Yes, there are frozen nitrogen plains orbiting in darkness beyond Neptune. They would probably assume you had consumed something medically concerning. Still, the Kuiper Belt remained hypothetical for decades because detecting objects there is incredibly difficult. These worlds are small, dark, and extremely far away. They reflect very little sunlight. Even large Kuiper Belt objects often appear fainter than distant stars, and because they move slowly against the background sky, spotting them requires careful observation over long periods. This is why astronomers missed the Kuiper Belt for so long, despite the fact that it contains enormous numbers of objects. The region is not hidden because it is tiny. It is hidden because space is absurdly large. Now, one important thing to understand is that the Kuiper Belt differs significantly from the asteroid belt located between Mars and Jupiter. People often compare the two because both contain many small bodies orbiting the Sun, but their compositions and histories are quite different. The asteroid belt mainly contains rocky and metallic objects. The Kuiper Belt contains icy bodies formed in much colder regions of the early solar system. And there is another major difference. The asteroid belt's current mass is surprisingly small. Scientists believe Jupiter prevented a planet from forming there by constantly disturbing material with its gravity. The Kuiper Belt, meanwhile, may once have contained far more mass than it does today. Some estimates suggest the early Kuiper Belt could have been dozens of times more massive than its present state. So where did all that material go? Gravity happened. More specifically, giant planet migration happened. This idea became central to modern theories about the outer solar system. According to the Nice model, the giant planets did not always occupy their current positions. Long ago, they likely shifted through the solar system as gravitational interactions redistributed energy and momentum. Neptune appears to have migrated outward significantly during this process. As Neptune moved, its gravity disrupted enormous numbers of icy objects. Some became trapped in resonances, some were scattered inward toward the Sun. Others were flung outward into distant regions beyond the Kuiper Belt itself, and many were ejected from the solar system entirely. Imagine a giant snowplow moving slowly through an icy field, scattering material in every direction. That is somewhat similar to what Neptune may have done billions of years ago. This explains why the Kuiper Belt today appears dynamically structured rather than evenly distributed. Astronomers divide Kuiper Belt objects into several categories based on their orbital behaviour. The classical Kuiper Belt contains objects following relatively stable orbits. Then there are resonant objects, including the Plutinos, trapped in orbital relationships with Neptune. And farther outward lie scattered disk objects travelling along elongated, unstable trajectories, likely created through past gravitational interactions. Some objects possess extremely tilted orbits. Others travel so far from the Sun that they blur the line between the Kuiper Belt and even more distant regions. The result is a solar system outskirts that feel less organised than the neat textbook diagrams most people grew up seeing. Reality, as usual, is messier and much more interesting. One particularly fascinating aspect of the Kuiper Belt involves colour. Oddly enough, many Kuiper Belt objects appear reddish. Not bright red exactly, more like dark rust-coloured tones. Scientists believe this. Coloration results from radiation interacting with frozen organic compounds over billions of years. Cosmic rays and ultraviolet sunlight slowly alter surface chemistry, producing complex carbon-rich materials called tholins. Tholins sound slightly like something a wizard would carry in a pouch, but they are real chemical substances and surprisingly important in planetary science. These compounds may resemble some of the organic chemistry present before life emerged on early Earth. That means the Kuiper Belt could preserve clues not only about planetary formation, but also about prebiotic chemistry throughout the solar system. Tiny frozen worlds drifting beyond Neptune may contain ingredients related to the chemistry that eventually allowed biology to emerge here on Earth. Which is quite a lot of responsibility for objects most people never think about. Now, another misconception about the Kuiper Belt involves density. Science fiction often portrays asteroid belts or debris regions as crowded obstacle courses, where spacecraft constantly dodge incoming rocks every few seconds. In reality, the Kuiper Belt is mostly empty space, enormously empty space. Even though millions of objects may exist there, the distances separating them are gigantic. If you travelled through the Kuiper Belt in a spacecraft, you would likely see absolutely nothing nearby for long stretches of time. This sometimes disappoints people. Human imagination prefers dramatic visuals, but the emptiness itself is part of what makes the outer solar system feel so strange. Picture standing on Pluto. The sun appears small and distant in the sky. Not tiny exactly, but far less dominant than it looks from Earth. Daylight resembles deep twilight compared to what we experience here. Around you stretches billions of kilometers of darkness scattered with frozen objects separated by unimaginable distances. No nearby planets hanging brightly overhead. No crowded skies. Just quiet. The outer solar system feels emotionally different somehow. Perhaps because sunlight there no longer fully controls the environment. On Earth, sunlight shapes almost everything we experience. Weather, temperature, ecosystems, daily rhythms. But out near the Kuiper Belt, solar warmth becomes weak and fragile. And yet the sun still rules everything gravitationally. That is another remarkable feature of the solar system. The sun's gravity reaches astonishing distances. Even objects tens of billions of kilometers away remain bound to it. The Kuiper Belt objects complete their orbits very slowly because of those immense distances. Pluto takes 248 Earth years to orbit the Sun once. Some more distant objects require thousands of years. Certain scattered objects may spend longer completing a single orbit than human civilization has existed. Imagine being born on Pluto and realizing your first birthday would not arrive for nearly 2.5 centuries. Admittedly, that would make age discussions very confusing. Happy first birthday, great-great-grandmother. Now, one reason scientists care so much about the Kuiper Belt is because it appears relatively primitive compared to the inner solar system. Earth, Venus, Mars, and the other rocky planets underwent intense geological evolution. Volcanoes reshaped surfaces, atmospheres changed, impacts altered landscapes repeatedly. But many Kuiper Belt objects remained frozen and relatively inactive. They preserve ancient conditions. In some cases, scientists believe these objects may contain material largely unchanged since the solar system formed 4.6 billion years ago. That makes the Kuiper Belt something like a cosmic freezer preserving original ingredients from the solar system's formation. And this preservation helps astronomers answer profound questions. How did planets form? How did giant planets migrate? How were comets created? What conditions existed in the early solar nebula? The Kuiper Belt contains evidence related to all of these mysteries. In fact, many short-period comets likely originate there. Comets are often described as dirty snowballs, which feels slightly unfair considering how spectacular they can look in the night sky. Still, the description is broadly accurate. They contain mixtures of ice, dust, and rocky material. When gravitational disturbances send Kuiper Belt objects inward toward the Sun, solar heating begins vaporizing their frozen surfaces. Gas and dust stream outward, forming glowing tails. So some of the comets humans admired throughout history may actually be former Kuiper Belt residents temporarily visiting the inner solar system. A frozen object drifting quietly beyond Neptune for billions of years suddenly plunges inward and becomes visible from Earth as a brilliant glowing streak in the sky. That transformation is rather dramatic. The Kuiper Belt also changed humanity's understanding of planetary categories themselves. Before its discovery, the solar system appeared relatively simple. 9 planets orbiting the Sun in tidy order. Then suddenly, astronomers discovered an entire population of worlds occupying the outer solar system. Some resembled Pluto, some rivaled Pluto in size, some challenged existing definitions entirely. This eventually led the International Astronomical Union to redefine the term planet in 2006, reclassifying Pluto as a dwarf planet. People still debate that decision today, which honestly says something lovely about humans. We become emotionally attached to distant icy worlds we have never visited. Still, scientifically, the discovery made sense because Pluto clearly belonged to a larger population rather than standing alone. And that larger population continues expanding as astronomers discover more objects every year. Some discoveries remain particularly puzzling. Sedna follows an orbit so elongated that it may have been influenced by passing stars long ago. Other objects cluster in ways that some astronomers interpret as possible evidence for an undiscovered giant planet, sometimes called Planet 9. Whether Planet 9 actually exists remains uncertain, but the fact that scientists seriously consider the possibility reveals how incomplete our understanding of the outer solar system still is. We have mapped continents on Earth more thoroughly than some regions beyond Neptune, and despite decades of observation, much of the Kuiper Belt remains unseen simply because objects there are so faint. There may be hundreds of thousands of bodies larger than 100 kilometers across waiting in the darkness, possibly millions of smaller ones, all orbiting silently beyond Neptune while life on Earth carries on completely unaware of them. Dinosaurs lived and vanished while these frozen objects continued circling the Sun. Human civilizations rose and fell, while Pluto completed only a fraction of one orbit. Even now, as you listen to this, countless icy bodies are moving through deep space in slow, ancient paths established billions of years ago. And the farther astronomers look into the Kuiper Belt, the more it stops feeling like the edge of the solar system and starts feeling like the beginning of something even larger waiting farther outward in the cold. One of the strangest things about the Kuiper Belt is that most people imagine it as much smaller than it really is. That is not because people are unintelligent. It is because the human brain evolved to understand forests, rivers, mountains, and walking distances. We are reasonably good at estimating how far away a tree might be or how long it takes to cross a city. But the outer solar system operates on scales so enormous that ordinary intuition simply gives up somewhere around Saturn and quietly walks away. Even astronomers occasionally describe these distances using comparisons because raw numbers stop feeling meaningful very quickly. For example, Earth sits about 150 million kilometers from the Sun. That distance already sounds enormous. Light itself, moving at roughly 300,000 kilometers per second, still requires over 8 minutes to reach us. Now imagine multiplying that distance by 30. That brings you roughly to the orbit of Neptune, and then imagine continuing outward even farther into darkness, where the Sun gradually shrinks into an intensely bright but emotionally distant point of light. That is where the Kuiper Belt begins. Not ends, begins. This is one of the biggest misconceptions about the outer solar system. People often picture Neptune as occupying the edge of known territory, with perhaps Pluto sitting slightly beyond it like a lonely afterthought. In reality, Neptune marks the entrance to an enormous frozen frontier extending billions of kilometers farther outward, and even defining exactly where the Kuiper Belt ends becomes surprisingly complicated. Astronomers usually describe the main Kuiper Belt as stretching from around 30 astronomical units to roughly 50 astronomical units from the Sun. Since 1 astronomical unit equals the average Earth-Sun distance, that means the main Kuiper Belt occupies a region spanning billions upon billions of kilometers. Already that is staggeringly large. But then things become messy, because the farther astronomers looked, the more objects they discovered moving beyond those traditional boundaries. Some worlds orbit well outside the main Kuiper Belt, yet still seem connected to it dynamically. Others travel in elongated paths carrying them incredibly far from the Sun before eventually returning inward again. The solar system does not end with a clean border, it fades outward gradually into increasingly mysterious territory. Now, one useful way to understand the Kuiper Belt's true size is to think about travel time rather than raw distance. When NASA launched New Horizons in 2006, it became the fastest spacecraft ever launched from Earth. Even moving at those extraordinary speeds, New Horizons still required nearly 9.5 years to reach Pluto. 9.5 years. And Pluto is not even near the farthest regions associated with the Kuiper Belt. After passing Pluto in 2015, New Horizons continued deeper into the outer solar system. In 2019, it flew past another Kuiper Belt object called Arrokoth. Arrokoth turned out to be one of the most extraordinary objects ever visited by a spacecraft because it looked unlike anything most people expected. Rather than a shattered chaotic rock, Arrokoth resembled 2 flattened icy lobes gently stuck together, almost like a cosmic snowman assembled in very slow motion. Scientists believe it formed extremely gently billions of years ago, preserving ancient conditions from the earlier solar system remarkably well. And importantly, Arrokoth sits even farther outward than Pluto, yet New Horizons still remains inside the broader outer solar system frontier. That gives you some sense of scale. Humanity's fastest spacecraft spent over a decade travelling outward and still barely scratched the surface of these distant regions. Another way to picture the Kuiper Belt's size is through sunlight itself. On Earth, sunlight feels immediate and dominant. It floods landscapes with brightness, creates weather systems, powers ecosystems, and warms surfaces quickly. At Pluto, sunlight is already around 1,600 times weaker than on Earth. Still bright enough to cast shadows, still unmistakably sunlight, but diminished. The sun there would no longer feel like an overwhelming presence filling the sky. Instead, it would appear more like an intensely brilliant star hanging in permanent twilight. And farther outward, the effect becomes even stranger. At 50 astronomical units, sunlight weakens dramatically again. Temperatures plunge toward extremes difficult to imagine properly. Water ice there behaves like solid rock. Meanwhile, substances we think of as gases on Earth freeze into permanent crusts and glaciers. Methane, nitrogen, carbon monoxide. The farther outward you travel, the more alien ordinary chemistry becomes. And still, the sun's gravity continues holding everything together. That is perhaps the most astonishing thing about the solar system. The sun's influence stretches unbelievably far. Now, technically speaking, the main concentration of Kuiper Belt objects decreases significantly, beyond roughly 50 astronomical units, because of something astronomers sometimes call the Kuiper Cliff. This sounds slightly dramatic, as though frozen objects suddenly tumble off a cosmic ledge into oblivion. In reality, it simply refers to the fact that astronomers observe far fewer objects beyond that distance than expected. For a while, scientists wondered whether this marked the true outer edge of the Kuiper Belt, but then objects kept appearing farther away, and farther and farther. Some belong to what astronomers call the scattered disk, a related but more dynamically chaotic region extending beyond the classical Kuiper Belt. Objects in the scattered disk often follow highly elongated orbits, likely created through gravitational interactions with Neptune long ago. These worlds can travel incredibly far from the Sun before slowly returning inward. One famous example is Eris. Eris follows an orbit carrying it between roughly 38 and 97 astronomical units from the Sun. 97 astronomical units. At that distance, sunlight takes over 13 hours just to arrive from the Sun. Imagine a sunrise so remote that the light illuminating your morning left the Sun before yesterday's breakfast on Earth. And even Eris is not the most distant object humans have identified. That title belongs to even stranger worlds. Perhaps the most famous is Sedna. Sedna barely behaves like a normal Kuiper Belt object at all. At its closest approach to the Sun, Sedna comes within roughly 76 astronomical units. But at its farthest point it may travel over 900 astronomical units away. 900. That number barely feels real. At Sedna's farthest distance, the Sun would appear simply as an extraordinarily bright star rather than a dominant solar disk. Daylight there would feel hauntingly dim compared to Earth. And Sedna's orbit takes around 11,000 years to complete once. To put that into perspective, the last time Sedna occupied roughly its current position, humans had not yet invented agriculture. Entire civilizations rise and disappear, while Sedna slowly drifts through a tiny fraction of one orbit. Objects like Sedna reveal something deeply important. The outer solar system is not neatly divided into clear regions. Instead, it transitions gradually outward into increasingly distant populations of icy bodies. Beyond the Kuiper Belt lies the scattered disk. Beyond that may exist the inner Oort cloud, and beyond even that eventually interstellar space itself. The scale becomes almost impossible to absorb emotionally. Now, interestingly, scientists believe the Kuiper Belt used to be much larger and far more massive than it appears today. Early in solar system history, enormous quantities of icy material likely orbited beyond the giant planets. But as Neptune migrated outward billions of years ago, its gravity destabilized huge numbers of objects. Some were thrown inward toward the Sun. Some became comets. Some were ejected from the solar system entirely. Others were scattered outward into distant, unstable orbits. The modern Kuiper Belt may therefore represent only a surviving fraction of a once much denser outer disk. That means the region we see today is already the thinned-out remnant after billions of years of gravitational reshaping, and despite that thinning, it remains enormous. One particularly difficult thing for humans to grasp is how empty enormous regions of space actually are. Science fiction often depicts asteroid belts as crowded obstacle courses, full of tumbling debris forcing pilots into constant evasive maneuvers. Reality is far quieter. If you travel through the Kuiper Belt in a spacecraft, you would probably spend most of your time surrounded by nothing visible at all. Objects are separated by immense distances, millions of kilometers, sometimes far more. Even in the denser regions, space itself dominates everything. The Kuiper Belt is both crowded and empty simultaneously. Crowded in terms of total objects, empty in terms of actual space between them. This emptiness affects exploration enormously. Finding Kuiper Belt objects requires careful telescopic surveys because many are tiny, dark, and faint. Some reflect only a small fraction of incoming sunlight. Others move so slowly across the sky that detecting their motion takes repeated observations over days or weeks, and there may still be countless undiscovered objects waiting farther outward. Astronomers estimate the Kuiper Belt could contain hundreds of thousands of bodies larger than 100 kilometers across, possibly millions of smaller objects, and yet humanity has only catalogued a fraction of them. The darkness hides them well. There is also something emotionally strange about how slowly everything moves out there. Inner planets race around the Sun comparatively quickly. Earth completes an orbit in 1 year. Jupiter takes about 12 years. But farther outward, orbital periods become enormous. Pluto needs 248 Earth years. Some scattered objects require thousands. and objects approaching the inner Oort cloud may need millions of years to complete one orbit around the Sun. The farther you move from the Sun, the more time itself seems to stretch. Not literally in the Einsteinian sense here, though relativity does exist quietly in the background. More psychologically, everything becomes slower, colder, dimmer, more ancient, and yet the outer solar system is not dead. That is another misconception. Several Kuiper Belt objects show evidence of geological activity. Pluto possesses glaciers and atmospheric cycles. Some dwarf planets may contain subsurface oceans insulated beneath layers of ice. Even at unimaginable distances from the Sun, processes continue. Worlds evolve, ice shifts, chemistry changes. The universe remains active almost everywhere. Now, another fascinating aspect of the Kuiper Belt's enormous extent involves gravity itself. The farther outward astronomers looked, the more they noticed certain strange orbital patterns among distant objects. Some orbits appeared oddly clustered in similar directions. This led to speculation about the possible existence of Planet 9. The idea remains controversial, but the basic argument is intriguing. Perhaps an undiscovered giant planet far beyond Neptune is gravitationally shaping distant Kuiper Belt objects. If Planet 9 exists, it may orbit hundreds of astronomical units from the Sun. That would push the known architecture of the solar system even farther outward. Again. This pattern keeps repeating throughout astronomy. Humans discover what seems like the edge. Then the universe quietly extends the map. For centuries, people thought the planets ended with Saturn, because Saturn was the farthest visible planet. Then came Uranus, then Neptune, then Pluto, then the Kuiper Belt, then the scattered disk, then strange detached objects like Sedna. Each discovery revealed that the solar system was not smaller and simpler than expected. It was larger and stranger, and perhaps still is. Because the farther astronomers search, the more the outer solar system starts resembling an enormous transitional zone, rather than a clean ending. A frontier fading gradually into interstellar darkness, and somewhere out there, beyond the main Kuiper Belt, beyond scattered icy worlds orbiting in deep cold, the Sun's influence slowly weakens until eventually another star's gravity becomes equally important. That boundary lies astonishingly far away. But even before reaching it, the Kuiper Belt itself already stretches across distances so large that human civilization, all of recorded history, every empire, language and generation, would fit comfortably inside only a tiny fraction of one orbit around those distant frozen worlds. Far beyond Neptune, where sunlight weakens into something pale and distant, entire worlds drift through darkness almost completely unnoticed. Not planets in the traditional sense, at least not according to modern astronomical definitions, but worlds nonetheless. Places with landscapes, seasons, moons, strange chemistry, and histories stretching back nearly to the birth of the solar system itself. And for most of human history, we had absolutely no idea they were there. That is one of the most remarkable things about the Kuiper Belt. It contains an enormous population of frozen objects hiding in plain sight against the night sky. They remained invisible not because they were especially secretive, but because they are incredibly dark, unimaginably distant, and scattered across a region so vast that even our best telescopes struggle to detect them. Some of these worlds are tiny fragments only a few kilometers across. Others are enormous dwarf planets with mountains, glaciers, and atmospheres, and almost all of them exist in permanent deep cold. Now, when most people picture distant space objects, they tend to imagine grey rocky surfaces like asteroids or moons. But many Kuiper Belt objects look very different because ice dominates their composition. Not just frozen water either. Out there, temperatures can drop below -220 degrees Celsius. At those temperatures, substances we normally think of as gases become frozen solid. Methane freezes, nitrogen freezes, carbon monoxide freezes. The chemistry of the outer solar system becomes wonderfully strange. Imagine landscapes where frozen nitrogen slowly moves across plains like glaciers on Earth. Mountains made not of rock, but hardened water ice behaving as solid bedrock because conditions are so cold. That sounds like science fiction. Yet we know such places exist because humanity has actually visited one. Before 2015, Pluto remained blurry even through powerful telescopes. Scientists could estimate its size and orbit, but the surface itself remained mysterious. Then New Horizons arrived, and suddenly Pluto transformed from a faint point of light into a real place. That moment changed how astronomers thought about the Kuiper Belt forever. Instead of dead, frozen rocks drifting through emptiness, New Horizons revealed a surprisingly active and complex world. Pluto possessed giant ice plains, mountain ranges, atmospheric haze layers, and evidence of glacial movement. One enormous region, called Sputnik Planitia, appeared almost completely free of impact craters, suggesting its surface had been resurfaced relatively recently in geological terms. That was astonishing. Tiny distant Pluto was not frozen in time after all. It still evolved. Its nitrogen ice slowly convected like thick lava lamps on unimaginably slow timescales. Glaciers shifted gradually across the landscape. Seasonal cycles altered atmospheric pressure. Even at the edge of the solar system, worlds remain dynamic, and Pluto is only one member of a much larger population. The Kuiper Belt contains countless frozen worlds hiding beyond easy observation. Some are large enough to qualify as dwarf planets. Others remain mysterious because they're so distant we barely know anything about them except their orbits and rough sizes. Still, each discovery adds another piece to the puzzle. Take Makemake, for example. Makemake is slightly smaller than Pluto and covered largely in methane ice. Its surface appears reddish, due to radiation interacting with frozen hydrocarbons over billions of years. This process creates complex organic materials called tholins, which coat many outer solar system objects in dark reddish hues. Tholin sounds slightly like something found in an expensive health smoothie, but in reality, they are important chemical compounds formed naturally in cold, radiation-rich environments. Scientists believe similar chemistry may have played a role in the early solar system before life emerged on Earth. So when astronomers study these frozen worlds, they are not merely cataloguing icy debris. They're examining ancient chemistry preserved in deep cold for billions of years. Another remarkable object is Haumea. Haumea barely looks spherical at all because it spins extraordinarily fast. A complete rotation takes less than 4 hours, stretching the dwarf planet into an elongated shape. Imagine Earth spinning so quickly that the entire planet visibly bulged outward. Haumea also possesses rings and multiple moons, making it one of the stranger worlds in the outer solar system. Scientists suspect Haumea experienced a gigantic collision long ago. That impact may have blasted icy fragments outward, creating an entire family of related Kuiper Belt objects, sharing similar compositions and orbital characteristics. Even at these immense distances, collisions shaped planetary history. Then there is Eris. Eris became famous partly because its discovery triggered the debate that ultimately led to Pluto's reclassification as a dwarf planet. At first, astronomers thought Eris might actually be larger than Pluto. Later measurements showed Pluto is slightly bigger in diameter, though Eris remains more massive. Still, the key issue was clear. If Pluto counted as a planet, then Eris probably should too. And if Eris qualified, perhaps several additional Kuiper Belt objects belonged on the planetary list as well. Suddenly, the solar system risked becoming crowded with new planets. Astronomers eventually chose instead to redefine the category itself, which people still argue about today with surprising emotional intensity. Humans become very attached to space objects, particularly underdog space objects. Now, despite all these discoveries, the overwhelming majority of Kuiper Belt worlds remain unseen in detail. Even the largest objects usually appear only as tiny points of light through telescopes. Their surfaces, geology and atmospheres remain mostly unknown. and many are extraordinarily dark. This surprises people sometimes because ice sounds reflective, but space weathering gradually darkens, surfaces over billions of years. Radiation alters chemistry, dust accumulates, organic compounds form. Some Kuiper Belt objects reflect only a small percentage of incoming sunlight. Trying to detect them from Earth is somewhat like searching for charcoal drifting through darkness billions of kilometers away. And the farther outward you look, the harder it becomes. Still, astronomers keep finding more objects every year. Some belong to the classical Kuiper Belt, following relatively stable orbits. Others travel along strange tilted paths influenced by ancient gravitational interactions with Neptune. Some possess moons, some rotate chaotically, some may even contain hidden internal oceans beneath frozen crusts. That possibility is especially intriguing. Here in the inner solar system, we often associate liquid water with warmth and sunlight. But surprisingly, some icy outer worlds may maintain underground oceans thanks to internal heating caused by radioactive decay or tidal interactions. Even far from the sun, warmth can survive beneath layers of insulating ice. It is a reminder that the universe rarely follows our intuitive expectations. Cold surfaces do not necessarily mean dead interiors. Now, perhaps the most emotionally strange thing about these frozen worlds is how ancient and isolated they are. Many Kuiper Belt objects formed over 4 billion years ago during the earlier stages of planetary formation. Unlike Earth, they experienced relatively little geological recycling. That means they preserve conditions from the solar system's childhood. While continents drifted on Earth, and life evolved through countless forms, these distant worlds simply continued orbiting slowly through darkness, almost unchanged. Dinosaurs lived and vanished during only a tiny fraction of Pluto's orbital period. Human civilization occupies an even smaller fraction. Some Kuiper Belt objects require hundreds or thousands of years to orbit the Sun once. Others take much longer. Time behaves differently out there psychologically. Everything feels slower. A sunrise on Pluto would not look hurried. Seasons last decades. Nitrogen frost slowly migrates across landscapes over immense spans of time. And because sunlight is so weak, even daytime appears dim compared to Earth. At Pluto's distance, the sun still shines brightly enough to cast shadows, but the light feels thin somehow, more like an intensely bright star suspended in twilight than the overwhelming solar presence we experience here. Farther outward, conditions become stranger still. Objects like Sedna venture so far from the sun that daylight there would appear profoundly dim. Sedna's orbit carries it out toward distances where the sun would no longer dominate the sky emotionally. It would simply be the brightest star among many. And Sedna is probably not alone. Astronomers suspect huge numbers of distant icy worlds remain undiscovered simply because they are too faint and remote for easy detection. Some may rival Pluto in size, possibly larger. There may even be undiscovered dwarf planets lurking far beyond current surveys. That possibility still feels wonderfully unsettling. Even after centuries of astronomy, the solar system remains partially unmapped. There are still entire worlds hiding in darkness beyond Neptune. One especially fascinating object visited by New Horizons after Pluto was Arrokoth. Arrokoth turned out to be unlike anything humans had seen before. It resembled two flattened icy bodies gently merged together. Scientists believe it formed through an incredibly gentle collision early in solar system history. Not a catastrophic smash. More like two drifting snowballs softly touching and sticking together. That matters enormously because it suggests some Kuiper Belt objects preserve extremely primitive structures dating back to the earlier stages of planetary formation. Arrokoth may resemble the original building blocks from which larger planets eventually formed. In a sense, it is a fossil from the solar system's construction era, and there may be countless similar objects still drifting unseen in the darkness. Now, another curious thing about these frozen worlds is their colour diversity. Some appear reddish, some grey, some surprisingly bright. These differences likely reflect variations in composition, radiation exposure, and impact history. Astronomers can often estimate surface materials by studying how objects reflect sunlight at different wavelengths. Even without direct photographs, light itself carries clues. It is rather impressive when you think about it. Humans sitting on one small planet around one ordinary star have figured out how to analyze the chemistry of distant icy bodies billions of kilometers away using tiny amounts of reflected light. And yet, despite all this progress, the Kuiper Belt still feels mysterious because it occupies a transitional zone between the known planetary system and the deeper outer darkness beyond. The farther outward scientists search, the less tidy the solar system becomes. Objects follow bizarre orbits, regions overlap, boundaries blur, and somewhere beyond these frozen worlds may lie even larger unseen structures, extending toward the hypothetical Oort cloud. But for now, the Kuiper Belt itself already contains enough frozen worlds to reshape humanity's understanding of the solar system completely. When most people hear the phrase dwarf planet, they immediately think of Pluto. That makes sense. Pluto became the most famous example after its reclassification in 2006, and for many people, it still carries an emotional identity somewhere between planet, exile, and tiny cosmic celebrity. But Pluto is not alone. Far beyond Neptune, hidden among the frozen debris of the Kuiper Belt, entire dwarf planets drift through darkness almost unnoticed by the wider world. Some are covered in methane frost. Some spin so quickly they become stretched into distorted shapes. Some possess moons. Some travel on bizarre elongated orbits carrying them unimaginably far from the sun, and all of them exist in conditions so cold and remote that sunlight itself begins to feel unfamiliar. Now, the term dwarf planet sounds slightly unfortunate. It has a strangely apologetic tone, as though the universe attempted to make a planet and then somehow forgot to finish the job properly. But scientifically, the category has a specific meaning. According to the International Astronomical Union, a dwarf planet is an object massive enough for gravity to pull it into a roughly spherical shape, but not massive enough to clear its orbital neighbourhood of other debris. That final requirement matters enormously. The 8 major planets dominate their orbital regions gravitationally. Smaller objects nearby either become moons, collide, or eventually get scattered away. But dwarf planets exist among populations of other objects rather than ruling their surroundings completely. Pluto, for example, lives inside the Kuiper Belt alongside countless neighbouring icy bodies. And once astronomers realised Pluto belonged to a much larger population, the category of dwarf planets suddenly expanded. The outer solar system turned out to contain entire worlds hiding in deep, cold. Some of them are remarkably strange. Let's begin with Pluto itself, because despite all the debate surrounding its classification, Pluto remains one of the most fascinating worlds humans have ever explored. Before New Horizons arrived in 2015, scientists knew surprisingly little about Pluto's surface. Through telescopes, it appeared only as a blurry reddish point of light. Then New Horizons flew past after nearly a decade of travel, and revealed something extraordinary. Pluto possessed towering mountains made of water ice. Glaciers of frozen nitrogen stretched across vast plains. Thin blue atmospheric hazes layered the sky. And one enormous region called Sputnik Planitia appeared geologically young and active. Pluto was not a frozen dead relic. It was a dynamic world. That realization changed the emotional feeling of the outer solar system somehow. Suddenly, these distant objects stopped feeling abstract. They became places. Cold places, certainly, but real ones. Pluto itself measures about 2,377 kilometers across, making it smaller than Earth's moon. Yet despite its modest size, it possesses remarkable complexity. Its atmosphere expands and contracts seasonally as Pluto moves along its elongated orbit. Nitrogen ice sublimates into gas and later freezes again as conditions change. Entire weather cycles happen there, albeit slowly and under dim sunlight. One especially interesting feature of Pluto is its moon Charon. Charon is enormous relative to Pluto's size. In fact, the two objects orbit a point located outside Pluto itself, creating something closer to a binary system than a traditional planet-moon relationship. Standing on Pluto, Charon would appear huge in the sky and remain fixed in place because the two worlds are tidally locked to one another. Imagine seeing the same moon hanging motionless overhead forever. No moonrise, no moonset, just permanent silent companionship in deep space. And beyond Pluto lie additional dwarf planets equally strange in their own ways. Consider Haumea. Haumea is one of the most bizarre objects in the outer solar system because it spins extraordinarily fast. One complete rotation takes less than 4 hours. That rapid spin stretches Haumea into an elongated shape resembling a flattened rugby ball rather than a sphere. Most large objects in space become rounded because gravity pulls matter inward evenly, but Haumea rotates so quickly that centrifugal force distorts its shape dramatically. It also possesses rings. Yes, even some dwarf planets have rings. The universe appears surprisingly fond of ring systems once you start paying attention. Scientists believe Haumea suffered a massive collision billions of years ago. That impact may have blasted icy fragments into space, forming both its moons and a family of related Kuiper Belt objects sharing similar compositions. So even out in the frozen darkness beyond Neptune, ancient collisions shaped planetary evolution. Then there is Makemake. Makemake possesses a reddish methane-covered surface and likely experiences seasonal atmospheric changes similar to Pluto's, though scientists are still studying it carefully. At these distances, observations become difficult. Even the largest dwarf planets remain tiny points of light through telescopes, and yet astronomers can still infer surprising amounts of information from reflected sunlight, orbital behaviour, and thermal measurements. It is one of the quieter miracles of modern science. Humans on one small planet studying frozen worlds billions of kilometres away using faint traces of light. Now perhaps the most controversial dwarf planet beyond Pluto is Eris. Eris became famous because its discovery triggered the debate that eventually redefined the term planet. At first, astronomers believed Eris might actually be larger than Pluto. Later measurements showed Pluto is slightly wider, though Eris remains more massive overall. Still, the essential problem remained. If Pluto counted as a planet, then Eris probably should too. And if Eris qualified, perhaps many additional Kuiper Belt objects deserved planetary status as well. Astronomers faced two choices: either dramatically expand the number of planets, or redefine the category itself. Eventually they chose redefinition. People still argue about it today. In fairness, Pluto's demotion felt emotionally personal to many, because humans had spent generations memorizing 9 planets in school. Pluto occupied a kind of symbolic role as the lonely little world at the edge of the solar system. Then suddenly, astronomers announced it belonged to a much larger population, scientifically reasonable, emotionally complicated. Now, what makes these dwarf planets especially fascinating is not merely their size, but their isolation. Most major planets dominate their environments. Earth sits surrounded mainly by empty orbital space. Jupiter controls huge numbers of moons and gravitationally influences vast regions around it. But dwarf planets exist among swarms of neighbouring objects. They are embedded within populations rather than standing apart from them. Pluto drifts among countless Kuiper Belt objects. Haumea belongs to an entire collisional family. Makemake shares the outer solar system with innumerable icy neighbours. Even Eris travels through distant scattered regions populated by other frozen bodies. The outer solar system feels less like a collection of isolated planets, and more like an enormous archipelago of icy worlds. And many remain undiscovered. That possibility still surprises people sometimes. We tend to assume modern astronomy has mapped the solar system thoroughly, Not even close. The farther beyond Neptune astronomers search, the more difficult detection becomes. Distant objects reflect tiny amounts of sunlight and move slowly across the sky. There may still be undiscovered dwarf planets lurking in the darkness, possibly several, perhaps more. Some may orbit at enormous distances where 1 year lasts thousands of Earth years. And farther outward still lies one of the strangest known objects in the solar system, Sedna. Sedna occupies an orbit so elongated and remote that astronomers still debate exactly how to classify it. At its closest approach to the Sun, Sedna comes within about 76 astronomical units. At its farthest, it may travel over 900 astronomical units away. That is extraordinarily distant. At such ranges, the Sun would no longer dominate the sky emotionally. It would appear simply as an exceptionally bright star. And Sedna's orbit takes roughly 11,000 years to complete. The last time Sedna occupied approximately its current position, humans had not yet developed organised agriculture. Entire civilizations unfold during tiny fractions of its orbital period. Sedna may represent part of a transitional region between the Kuiper Belt and the much more distant hypothetical Oort cloud. Its strange orbit raises fascinating possibilities. Perhaps passing stars disturbed it long ago while the Sun still resided inside its birth cluster. Perhaps unseen planets influenced it. Or perhaps the outer solar system remains more complicated than we currently understand. That last explanation appears increasingly common in astronomy. Now, another remarkable thing about dwarf planets in the outer solar system is how ancient they are. Unlike Earth, which constantly reshapes itself through tectonic activity, erosion and weather, many dwarf planets preserve ancient surfaces and chemistry dating back billions of years. They are cosmic time capsules, frozen remnants from the solar system's formation. And despite their isolation, they may contain clues about processes that shape the entire planetary system. For example, many dwarf planets contain large amounts of water ice mixed with complex organic molecules. Some may harbour subsurface oceans beneath insulating crusts. That possibility becomes especially intriguing because liquid water hidden beneath ice appears surprisingly common throughout the solar system. Even in deep cold, internal heating can persist. Worlds that look frozen and inactive from space may conceal oceans beneath their surfaces. The universe repeatedly demonstrates that appearances are unreliable. Now, emotionally speaking, there is something deeply strange about imagining these dwarf planets drifting through darkness for billions of years. No sunlight warming their surfaces meaningfully. No nearby planets filling the sky. Just faint distant starlight and the dim glow of the faraway sun. And yet they continue orbiting patiently. Year after year, century after century, orbit after orbit. Some possess seasons lasting decades or centuries because of their elongated orbits and tilted rotational axes. On Pluto, for instance, entire generations of humans can pass during a single seasonal cycle. Time stretches outward in the Kuiper Belt. Everything moves more slowly there. Even sunlight seems reluctant. And still, these frozen worlds matter enormously because they preserve evidence from the solar system's earliest history. Studying them helps astronomers understand how planets formed, how giant worlds migrated, and how icy bodies evolved over billions of years. The dwarf planets of the outer solar system are not failed planets or incomplete leftovers. They are survivors, ancient worlds still circling the sun at the edge of darkness, while the rest of the solar system changed dramatically around them. And somewhere beyond the known dwarf planets, farther out in regions barely explored at all, additional frozen worlds may still be waiting silently in the cold, hidden from view beneath the enormous darkness beyond Neptune. One of the strangest things about the Kuiper Belt is that it manages to feel empty and crowded at exactly the same time. That sounds contradictory at first. After all, something should either contain many objects or very few. A forest is crowded, a desert is empty. A parking lot at 3 a.m. is empty unless one suspicious van remains parked under a flickering light, which immediately changes the emotional atmosphere entirely. But space does not follow ordinary human instincts about density and distance. The Kuiper Belt contains an enormous population of icy worlds and fragments orbiting beyond Neptune. Astronomers estimate there may be hundreds of thousands of objects larger than 100 kilometers across and possibly millions of smaller bodies. That sounds crowded, yet if you actually travelled through the Kuiper Belt in a spacecraft, you would probably spend most of your journey seeing absolutely nothing nearby at all. No dramatic obstacle fields, no endless tumbling rocks, no desperate evasive manoeuvres every few seconds like science fiction tends to suggest. Mostly darkness, immense darkness, and scattered objects separated by millions of kilometers. This disconnect between perception and reality happens because humans evolved in environments where many things usually means those things exist relatively close together. But the Kuiper Belt occupies a region so staggeringly large that even enormous numbers of objects become diluted across incomprehensible distances. Now, when people imagine asteroid belts or debris fields, they often picture something like a cosmic traffic jam. This misconception exists partly because movies need visual excitement. A realistic asteroid belt would mostly involve staring through windows at empty space, while occasionally noticing one distant rock very far away. Not exactly thrilling cinema. In reality, even the asteroid belt between Mars and Jupiter is extremely sparse. Spacecraft have crossed it many times without difficulty. The Kuiper Belt is vastly larger and even more spread out. That emptiness becomes easier to appreciate when considering scale properly. The main Kuiper Belt stretches roughly from 30 to 50 astronomical units from the Sun. One astronomical unit equals about 150 million kilometers, so we're discussing a region billions of kilometers wide. And unlike a flat ring drawn in textbooks, the Kuiper Belt also possesses thickness. Objects orbit at different inclinations above and below the solar system's plane, creating a three-dimensional structure rather than a thin disk. That increases the available volume enormously. Imagine throwing a handful of grains across an entire continent. Even though many grains exist, they would still feel isolated from one another. That is somewhat similar to the Kuiper Belt, and yet despite all that emptiness, astronomers still describe the region as crowded because so many objects inhabit it, compared to the surrounding space. The outer solar system beyond Neptune is not empty vacuum with only Pluto drifting alone. It contains a huge population of icy bodies sharing related origins and orbital behaviours. The crowd exists statistically rather than visually. Now, interestingly, the Kuiper Belt may actually be far less crowded today than it used to be. This is one of the most important discoveries in modern planetary science. Astronomers believe the early Kuiper Belt likely contained much more material billions of years ago. Some models suggest it may once have possessed tens of times its current mass. That means the ancient outer solar system was probably far denser than what we see now. So what happened? Gravity happened. More specifically, giant planet migration happened. According to the Nice model, the giant planets formed in somewhat different positions than where they orbit today. Over time, gravitational interactions caused the planets to shift. Neptune migrated outward into the outer disk of icy objects, and as Neptune moved, it disrupted enormous numbers of bodies gravitationally. Some objects became trapped in orbital resonances, some were flung inward toward the Sun, some became comets, some were ejected from the solar system entirely, and others were scattered into distant unstable orbits far beyond the classical Kuiper Belt. In other words, the modern Kuiper Belt may represent only a surviving remnant of a once much more crowded ancient structure. That idea changes how the outer solar system feels emotionally somehow. The quiet, frozen frontier we see today may actually be the leftover debris after billions of years of gravitational rearrangement. A thinned-out survivor population. Now, another fascinating reason the Kuiper Belt feels simultaneously crowded and empty involves the strange way gravity organises object there. The Kuiper Belt is not uniformly distributed. Certain regions contain concentrations of objects trapped in resonances with Neptune. Others appear relatively depleted. This creates invisible gravitational architecture shaping the entire region. Pluto itself provides one of the best examples. Pluto follows a 3-to-2 resonance with Neptune. For every 3 Neptune orbits, Pluto completes exactly 2. This synchronized relationship prevents collisions despite overlapping orbital distances. Many additional Kuiper Belt objects share similar resonances and are collectively known as plutinos. Again, slightly adorable terminology for frozen ancient worlds. There are also objects in 2-to-1 resonances and several other orbital patterns controlled by Neptune's gravity. This means the Kuiper Belt is not random debris drifting aimlessly. It contains structure, invisible gravitational rhythms, and those rhythms create regions where objects cluster more densely while leaving gaps elsewhere. In some ways, it resembles cosmic choreography more than chaos, although admittedly extremely slow choreography involving ice and billions of years. Now perhaps the strangest example of emptiness within the Kuiper Belt is something astronomers call the Kuiper Cliff. This refers to the surprisingly sharp drop in the number of observed objects beyond roughly 50 astronomical units. For a while, scientists expected the Kuiper Belt to continue smoothly outward. Instead, the population appears to thin dramatically. Why? That remains partly mysterious. Perhaps Neptune's migration disrupted outer regions long ago. Perhaps planet formation became less efficient farther from the Sun. Or perhaps we simply have not observed enough distant objects yet because detection becomes increasingly difficult with distance. The farther outward you search, the fainter everything becomes. And these objects are already incredibly dim. Most Kuiper Belt objects reflect very little sunlight. Many possess dark reddish surfaces altered by radiation over billions of years. Even large bodies often appear only as faint moving points through powerful telescopes. Trying to map the Kuiper Belt is somewhat like searching for charcoal, drifting through darkness from billions of kilometers away. Humanity has discovered thousands of Kuiper Belt objects so far, but that likely represents only a fraction of what actually exists. There may still be many large undiscovered bodies hiding in the outer darkness, possibly even additional dwarf planets. That uncertainty matters because it reminds us how incomplete our understanding of the solar system still is. People often assume the solar system has been fully mapped. Not remotely. There are still enormous regions beyond Neptune where unknown worlds may drift unseen, and the farther outward astronomers look, the stranger orbital patterns become. Objects like Sedna occupy bizarre elongated orbits, carrying them extraordinarily far from the Sun. Sedna itself travels so far outward that some astronomers consider it part of a transitional region between the Kuiper Belt and the hypothetical Oort cloud. Its orbit remains difficult to explain fully. Some researchers suspect passing stars may have influenced Sedna long ago, when the Sun still resided inside its birth cluster. Others speculate about hidden planets shaping distant objects gravitationally, which brings us to the famous Planet 9 hypothesis. Certain distant Kuiper Belt objects display orbital clustering that some astronomers interpret as evidence for a large unseen planet far beyond Neptune. The proposed planet, if real, might orbit hundreds of astronomical units from the Sun. That would extend the solar system's known architecture dramatically farther outward once again. Still, Planet 9 remains hypothetical. Astronomers continue searching carefully. And honestly, there is something wonderfully fitting about the possibility that the outer solar system may still contain undiscovered planets hiding in darkness. The farther humanity explores space, the less complete the map seems to become. Now, another curious aspect of the Kuiper Belt's emptiness involves collisions. Despite containing many objects, collisions today are relatively rare because distances between bodies are so large, but billions of years ago, when the region was denser, impacts likely occurred far more frequently. Evidence of those ancient collisions remains visible. Haumea, for instance, appears to be the result of a giant impact long ago. Its rapid rotation an associated family of icy fragments strongly suggest a violent collisional history. Even in the cold outskirts of the solar system, worlds crash together, and some of the debris from those ancient collisions still drifts through the Kuiper Belt today. One especially remarkable object visited by New Horizons was Arrokoth. Arrokoth looked unlike anything humans expected. Two flattened lobes gently merged together, preserving evidence of extremely slow and delicate formation processes. Scientists believe Arrokoth formed through a gentle collision early in solar system history, rather than a violent impact. That discovery suggested at least some Kuiper Belt objects preserve ancient primordial structures remarkably well. In other words, the Kuiper Belt contains both evidence of destruction and evidence of delicate survival, chaos and preservation together. Now, emotionally speaking, the Kuiper Belt's emptiness creates a peculiar atmosphere difficult to describe properly. The inner solar system feels busy. Planets move relatively quickly. Sunlight dominates everything. Moons, rings, storms, and magnetic fields create dynamic environments. But beyond Neptune, the pace changes. Objects drift slowly through dim sunlight. Orbital periods stretch into centuries or millennia. Distances between worlds become immense. The darkness itself begins feeling almost physical. And yet hidden inside that emptiness are countless frozen worlds, ancient debris fields, dwarf planets, and orbital structures shaped by gravity over billions of years. The Kuiper Belt is not an empty void, nor is it a crowded obstacle course. It is something stranger. A sparse, frozen frontier filled with ancient objects separated by enormous silence, all slowly orbiting the sun together at the edge of the known planetary system. Billions of years ago, before Earth had oceans, before Jupiter possessed its familiar storms, and long before anything remotely resembling life existed anywhere in the solar system, our cosmic neighborhood looked very different from the orderly arrangement we know today. There were no stable planetary orbits yet, no calm separation between rocky inner worlds and icy outer regions, no familiar map showing planets lined up neatly around the sun. Instead, the young solar system was chaotic, crowded, violent, and filled with drifting material moving in every direction around a newborn star. And out of that chaos came the Kuiper Belt, not as a carefully designed structure, but as a surviving remnant, a frozen collection of leftovers preserving evidence from the solar system's earliest construction era. That word leftovers might sound dismissive at first, as though the Kuiper Belt consists merely of unwanted debris forgotten after the planets finish forming. But in planetary science, leftovers are often the most valuable evidence. Imagine archaeologists uncovering fragments around an ancient city, broken pottery, discarded tools, scraps of material left behind during construction. Those fragments may reveal more about daily life than the grand buildings themselves. The Kuiper Belt works similarly. It preserves ancient material from the solar system's formation that never fully became part of a major planet. And because many Kuiper Belt objects remained relatively unchanged for billions of years, they function almost like cosmic fossils. To understand why this matters, we need to travel back to the beginning of the solar system itself. Around 4.6 billion years ago, the Sun did not yet exist as a stable star. Instead, a giant molecular cloud of gas and dust drifted through part of the Milky Way. At some point, something disturbed this cloud, possibly a nearby supernova explosion, perhaps gravitational interactions with neighbouring material. Whatever the trigger, regions within the cloud began collapsing under gravity. As the cloud contracted, it started spinning faster. This happens naturally whenever collapsing material conserves angular momentum. Ice skaters pulling their arms inward spin more quickly. The same principle applies to collapsing gas clouds on astronomical scales. Gradually, the material flattened into a rotating disk surrounding a dense central region that would eventually ignite as the Sun. This structure became known as the solar nebula. And inside that enormous rotating disk, countless tiny particles began colliding. Dust grains stuck together electrostatically. Pebbles formed, then rocks, then larger bodies called planetesimals. Over time, gravity took over more strongly. Larger objects attracted additional material, growing steadily through collisions and accumulation. Planet formation had begun. Now conditions varied dramatically depending on distance from the young sun. Closer inward, temperatures were extremely high. Volatile substances like water, methane and ammonia could not remain frozen. Only metals and rocky minerals survived easily. That is one reason the inner planets became relatively small rocky worlds. Farther outward, however, temperatures dropped enough for ices to remain stable, and this changed everything. Beyond a certain distance called the frost line, enormous amounts of frozen material became available for planet formation. Water ice alone dramatically increased the amount of solid matter in the outer solar nebula. That allowed giant planetary cores to grow rapidly. Jupiter likely formed first. Once its core reached sufficient mass, it began capturing huge amounts of hydrogen and helium gas from the surrounding nebula. Soon Saturn followed, then Uranus and Neptune. The giant planets emerged quickly and powerfully, and their gravity reshaped the solar system permanently. This is where the story becomes especially important for understanding the Kuiper Belt, because the giant planets did not simply form and stay politely where they started, they moved. Modern planetary science strongly suggests the giant planets migrated significantly during the solar system's early history. Their gravitational interactions with surrounding material altered their orbits over time. According to the Nice model, named after the French city where it was developed, Neptune originally formed much closer to the Sun than it occupies today. Then gradually, through countless gravitational encounters with smaller icy bodies, Neptune migrated outward. Imagine pushing through a crowd. Each interaction transfers tiny amounts of momentum. Eventually large-scale movement occurs. Neptune essentially did this on a planetary scale. As Neptune moved outward, it scattered enormous numbers of icy planetesimals throughout the outer solar system. Some objects were thrown inward, some outward, some completely ejected into interstellar space. Others became trapped in resonances, and many eventually formed the populations we now recognize as the Kuiper Belt and scattered disk. This means the Kuiper Belt is not merely a random accumulation of debris, it is evidence of giant planetary migration, a surviving record of ancient gravitational upheaval. Now, one fascinating consequence of this migration involves orbital resonances. As Neptune moved outward, its gravity captured certain objects into synchronized orbital relationships. Pluto provides the classic example. Pluto follows a 3-to-2 resonance with Neptune. For every 3 Neptune orbits around the Sun, Pluto completes exactly 2. This resonance protects Pluto from collisions despite overlapping orbital distances. Many additional Kuiper Belt objects share similar resonances. These Plutinos preserve evidence of Neptune's migration billions of years ago. Gravity left fingerprints throughout the outer solar system, and those fingerprints remain visible today. Now, interestingly, the early outer solar system was probably far more crowded than it appears now. The primordial Kuiper Belt may once have contained many times its current mass. Some estimates suggest dozens of Earth masses worth of icy material originally occupied those regions. Today, however, the total mass of the Kuiper Belt appears surprisingly small. So where did everything go? Mostly into space. During planetary migration, giant planets scattered enormous quantities of material away. Some objects plunged inward toward the Sun. Others were ejected completely from the solar system. Jupiter in particular behaves somewhat like a gravitational bouncer at the entrance to the solar system. Its immense gravity either redirects incoming objects dramatically or throws them outward entirely. Without Jupiter, the solar system might look profoundly different today. In fact, some astronomers suspect giant planet migration may even have triggered the late heavy bombardment. a period roughly 4 billion years ago when impacts throughout the inner solar system increased dramatically. If true, then the outer solar system helped shape Earth's early history directly. Some of the ancient impactors striking the young Earth may have originated from populations disrupted during giant planet migration, possibly even material related to the early Kuiper Belt. That idea carries a strange emotional weight. Tiny frozen objects drifting beyond Neptune today may be distant relatives of bodies that once crashed into Earth during the planet's violent youth. The solar system is more interconnected than it first appears. Now, despite all this chaos, not everything was destroyed or scattered away. Some objects survived relatively undisturbed, and those survivors became incredibly valuable scientifically. Because unlike Earth, many Kuiper Belt objects experienced very little geological recycling. Their surfaces and compositions preserve ancient conditions dating back nearly to the solar system's formation. That makes them extraordinary natural archives. One particularly important example is Arrokoth. When New Horizons flew past Arrokoth in 2019, scientists were astonished by what they saw. Arrokoth resembled two flattened icy lobes gently joined together, not shattered, not violently deformed. Instead, it appeared to preserve evidence of extremely gentle formation processes from the early solar nebula. Scientists believe Arrokoth likely formed when two smaller bodies slowly drifted together and merged softly rather than colliding catastrophically. That discovery mattered enormously because it suggested some Kuiper Belt objects preserved primordial structures almost unchanged for billions of years. Arrokoth may resemble the original building blocks from which planets formed, a surviving fossil from the solar system's earliest construction era. And there are probably countless additional primordial objects still drifting unseen in the outer darkness. Now, another important role of the giant planets involves comet formation. Many short-period comets likely originate from the Kuiper Belt or related scattered populations. Gravitational disturbances occasionally send icy objects inward toward the Sun. As these objects approach warmer regions, solar heating vaporizes frozen materials, creating glowing comas and tails. So some of the comets admired throughout human history may actually be ancient leftovers from planetary formation itself. Tiny survivors from the solar system's beginning temporarily visiting the inner planets before retreating outward again. There is something strangely poetic about that, though not in a dramatic sense. More in the quiet realization that the solar system still circulates ancient material billions of years after its formation. The past continues orbiting around us. Now, perhaps the most remarkable thing about the Kuiper Belt is how it transformed humanity's understanding of the solar system. Before its discovery, many people imagined the solar system as relatively simple. Planets orbiting the Sun in orderly fashion with Pluto sitting alone at the outer edge. But the Kuiper Belt revealed something much larger and more complicated. The solar system does not end neatly. Beyond Neptune exists an enormous surviving population of icy bodies, preserving evidence from the earlier stages of planetary evolution. And the farther astronomers look, the more they discover additional layers of structure. Scattered disk objects, detached objects like Sedna, possibly even undiscovered planets still hiding in distant darkness. Each new discovery pushes the map farther outward, and through it all the giant planets remain central characters in the story. Without Jupiter, Saturn, Uranus, and Neptune migrating through the young solar system, the Kuiper Belt might never have formed in its current structure at all. Those giant worlds sculpted the outer solar system gravitationally. They scattered objects, trapped resonances, created gaps, altered trajectories, and reshaped entire populations of icy bodies. The frozen worlds drifting beyond Neptune today are not random leftovers. They are survivors of ancient planetary rearrangement. Fragments of a chaotic era preserved in deep cold at the edge of sunlight, while the rest of the solar system gradually settled into the quieter arrangement we know today. Out beyond Neptune, the solar system begins behaving less like a neat mechanical clock and more like an enormous gravitational wilderness. The farther astronomers looked into the Kuiper Belt, the more unusual the orbits became. Some objects travel in smooth, relatively stable paths. Others tilt sharply above or below the plane of the solar system. Some follow stretched elliptical trajectories, carrying them unimaginably far from the sun before they slowly drift back inward again. And a few objects move in ways so strange that astronomers still debate what invisible forces might be shaping them. This is where the outer solar system starts feeling genuinely mysterious. Not mysterious in a dramatic science fiction sense involving glowing portals or ancient alien machines hidden in darkness. Real astronomy is usually quieter than that. Instead, it is mysterious because gravity leaves clues without immediately revealing the full story behind them, and the deeper scientists study these distant orbits, the more they realize the solar system's outer boundary is far less orderly than earlier generations imagined. For centuries, humans assumed the planets followed clean, predictable paths around the sun, and that the solar system probably ended not far beyond the outermost visible world. Then telescopes improved, and suddenly the map kept expanding. First came Uranus, then Neptune, then Pluto, then the Kuiper Belt itself. And once astronomers began discovering huge numbers of distant icy objects, another realization followed quickly. The outer solar system was not calm. It was dynamically complicated. Now, one important thing to understand is that orbits in space are rarely fixed forever. Gravity constantly influences everything. Large planets tug on smaller objects. Passing stars can alter distant trajectories. Collisions change momentum. Even tiny repeated gravitational interactions over millions or billions of years can gradually reshape orbital paths. The outer solar system is essentially a giant, long-term gravitational experiment running for billions of years, and some of the results became very strange indeed. Take Pluto's orbit, for example. Compared to the major planets, Pluto behaves oddly. Its orbit is tilted significantly relative to the solar system's main plane, and it follows a highly elongated path around the Sun. At certain points, Pluto actually comes closer to the Sun than Neptune does. That sounds unstable at first. Surely crossing orbital distances should eventually lead to disaster, but Pluto survives because it occupies a stable resonance with Neptune. For every 3 Neptune orbits, Pluto completes exactly 2. This synchronized timing prevents collisions. Whenever Pluto crosses Neptune's orbital distance, Neptune itself is always somewhere else. The arrangement resembles an incredibly slow gravitational dance lasting billions of years. And Pluto is not unique. Astronomers discovered many additional objects trapped in resonances with Neptune. These resonant populations preserve evidence of the giant planet's ancient migration through the outer solar system. But beyond these relatively stable resonances lies something far more chaotic: the scattered disk. Scattered disk objects follow extremely elongated and unstable orbits, likely created when Neptune migrated outward billions of years ago. As Neptune moved, its gravity flung icy bodies into strange trajectories. Some objects were ejected from the solar system entirely. Others ended up in highly stretched orbits extending far beyond the classical Kuiper Belt. These scattered worlds spend most of their existence drifting through deep darkness. Then slowly, over centuries or millennia, they swing closer toward the Sun again before retreating outward once more. One especially famous example is Eris. Eris follows a dramatically elongated orbit carrying it between roughly 38 and 97 astronomical units from the Sun. At its farthest point, sunlight there becomes extraordinarily weak. The Sun would appear more like an intensely bright star than the dominant blazing object we experience on Earth, and still Eris remains gravitationally bound to it. That alone feels astonishing somehow. The Sun's influence reaches enormous distances. Now, farther outward still lies one of the strangest known objects in the solar system, Sedna. Sedna does not fit comfortably into existing categories. It travels on an orbit so large and elongated that astronomers still debate exactly how it reached its current trajectory. At closest approach, Sedna comes within about 76 astronomical units of the Sun. At its farthest point, however, it may travel beyond 900 astronomical units. 900. That number barely feels emotionally real. At those distances, the Sun would no longer dominate the sky visually. It would appear simply as the brightest star among countless others, and Sedna's orbital period lasts around 11,000 years. The last time Sedna occupied approximately its current position, human civilization as we know it did not yet exist. Agriculture had not begun, cities had not formed. Entire chapters of human history occupy tiny fractions of one Sedna year. Now, Sedna's strange orbit raises major questions because it remains difficult to explain using the known planets alone. Normally, distant icy objects approaching Neptune can be scattered through gravitational interactions, but Sedna never comes close enough to Neptune for that explanation to work easily. Something else appears to have influenced it, possibly several things. One idea involves passing stars. Astronomers believe the Sun likely formed inside a dense stellar nursery alongside many neighbouring stars. During those early millions of years, close stellar encounters may have disturbed distant icy objects gravitationally. A passing star could potentially stretch or redirect orbits like Sedna's. Another possibility involves unseen planets farther outward, and this is where the famous Planet 9 hypothesis enters the story. Over the past decade, astronomers noticed something peculiar about several extremely distant Kuiper Belt and scattered disk objects. Their orbits appeared oddly clustered, not randomly distributed. Certain orbital alignments seemed too similar to be entirely coincidental. That raised a fascinating possibility. Perhaps a large unseen planet far beyond Neptune is gravitationally shaping these objects over immense timescales. The hypothetical world became known as Planet 9. According to some models, Planet 9 might possess several times Earth's mass and orbit hundreds of astronomical units from the Sun. If real, it would take thousands or perhaps tens of thousands of years to complete a single orbit. At such distances, sunlight would be incredibly dim. The planet itself would remain extraordinarily difficult to detect, and importantly, Planet 9 remains hypothetical. No one has actually seen it. Astronomers continue searching carefully using powerful telescopes, examining enormous regions of sky for faint moving objects. Some researchers believe the orbital clustering evidence is convincing. Others argue the observed patterns may result from observational bias or incomplete data. The debate remains active. Still, the fact that scientists seriously consider the possibility of another giant planet hiding in the outer solar system reveals something remarkable. Even now, humanity may not fully know what exists in its own planetary system. That realization carries a strange mixture of humility and excitement. We often imagine astronomy as a completed map. In reality, much of the outer solar system remains only partially explored. Now, another curious feature of these distant objects involves orbital inclination. Many Kuiper Belt objects follow paths tilted significantly relative to the solar system's main plane. Some travel at steep angles entirely unlike the nearly flat orbits of the major planets. Why? Again, ancient gravitational chaos appears responsible. Planetary migration, collisions, and scattering events gradually pumped energy into these orbits over billions of years. The outer solar system became dynamically heated, meaning orbital motions grew more chaotic and varied. Certain objects may even flip into retrograde orbits, moving opposite the general direction of planetary motion. The farther outward astronomers look, the less tidy the solar system appears, and perhaps that makes sense. Closer to the Sun, gravity from the major planets dominates strongly, maintaining relatively stable order. Farther outward, the Sun's grip weakens gradually. Orbital timescales lengthen enormously. External influences become more important. The edge of the solar system begins blurring into the broader gravitational environment of the galaxy itself. That transition zone feels emotionally strange somehow. On Earth, boundaries usually appear clear. A coastline, a fence, a city limit. But the solar system does not truly end with a hard border. Instead, it fades gradually outward through increasingly distant and loosely bound populations of icy bodies. Beyond the Kuiper Belt lies the scattered disk. Beyond that may exist the inner Oort cloud. And farther still, eventually interstellar space itself. The boundaries are soft. Now, despite all this orbital chaos, some distant objects remain surprisingly stable. Certain resonant populations survive for billions of years because gravitational relationships protect them. Others occupy relatively calm regions called the cold classical Kuiper Belt. These objects follow low-inclination stable orbits and may preserve especially ancient primordial conditions. One object explored by New Horizons called Arrokoth likely belongs to this population. Arrokoth appeared remarkably primitive and undisturbed, preserving evidence of gentle early formation processes. Its existence suggests parts of the outer solar system remained relatively quiet despite all the broader chaos. So the Kuiper Belt contains both stability and disorder simultaneously. Ancient untouched survivors drifting alongside objects flung into bizarre trajectories by gravitational violence long ago. And that contrast makes the outer solar system feel deeply alive dynamically. Not alive biologically perhaps, though hidden oceans remain possible beneath some icy worlds. Alive gravitationally. Every orbit tells part of a story. Some reveal ancient planetary migration. Some preserve evidence of collisions. Some hint at unseen influences still shaping distant regions. And a few raise questions astronomers still cannot fully answer. That uncertainty is important. Science often advances not through certainty but through anomalies, strange data points, unexpected patterns, objects refusing to behave exactly as predicted. The outer solar system contains many such anomalies: Sedna, detached objects, orbital clustering, possible unseen planets. Even now, astronomers continue discovering new distant worlds with surprising trajectories. And every discovery reminds us the edge of the solar system is not a quiet, frozen ending. It is a vast, poorly understood frontier shaped by gravity, time, migration, and invisible influences stretching outward into darkness far beyond Neptune. Long before astronomers understood the existence of the Kuiper Belt, comets were already visiting the inner solar system, like mysterious messengers arriving from somewhere beyond the known planets. For most of human history, people had no idea what comets actually were. Some civilizations viewed them as omens. Others believed they announced disasters, wars, or the deaths of kings. Ancient sky watchers recorded strange glowing objects appearing suddenly in the heavens, growing bright tails across the night sky before eventually fading away again into darkness. And honestly, given what people knew at the time, the reactions were understandable. Comets do look unsettling. Unlike stars, they move. Unlike planets, they suddenly grow enormous glowing tails stretching across the sky. And unlike ordinary celestial objects, they seem unpredictable. Even the word comet carries something slightly uneasy about it. But modern astronomy eventually revealed that comets are not supernatural warnings or wandering fires in the heavens. They are ancient icy bodies, frozen leftovers from the solar system's formation, and many of them likely come directly from the Kuiper Belt itself. That realization transformed comets from mysterious visitors into important scientific clues about the outer solar system. Now, at first glance, comets and Kuiper Belt objects may not seem closely connected. One appears as dramatic, glowing objects streaking through the inner solar system with enormous luminous tails. The other sounds more like a quiet frozen population drifting far beyond Neptune. But in many cases, they are essentially the same kinds of objects observed under very different conditions. The crucial difference is sunlight. Out in the Kuiper Belt, temperatures remain incredibly cold. Water ice stays frozen permanently. So do methane, ammonia, nitrogen, and other volatile compounds. Kuiper Belt objects simply drift quietly through darkness with little visible activity. But when gravitational interactions alter an orbit and send one of these icy bodies inward toward the Sun, everything changes. As the object approaches warmer regions, solar heating begins vaporizing frozen material. Gas erupts from the surface, dust gets released into surrounding space. Sunlight and solar wind then shape this material into glowing tails stretching millions of kilometers across. A comet is born, or more accurately revealed. In many ways, comets are simply Kuiper Belt objects temporarily transformed by heat and sunlight. Now, astronomers divide comets into different categories, depending largely on their orbital periods. Long-period comets arrive from extremely distant regions and may originate in the hypothetical Oort cloud. These comets can take thousands or even millions of years to orbit the Sun once. But short-period comets behave differently. They follow shorter, more predictable orbits, lasting less than about 200 years. Many travel in paths aligned relatively closely with the plane of the solar system. And this is where the Kuiper Belt becomes extremely important. Scientists now believe many short-period comets originated there. More specifically, they likely began as Kuiper Belt objects before gravitational interactions gradually altered their trajectories. Often, Neptune plays a major role in this process. Objects drifting through the outer solar system occasionally pass close enough to Neptune for its gravity to reshape their orbits. Some become scattered inward toward the giant planets. Additional gravitational encounters then continue redirecting them closer to the Sun. Eventually, one of these ancient icy bodies may plunge inward far enough for solar heating to activate it. And suddenly, something that spent billions of years nearly invisible in deep cold becomes one of the brightest objects in Earth's sky. That transformation is rather astonishing when you think about it. A tiny frozen world drifting silently beyond Neptune for billions of years suddenly grows a glowing tail visible to human eyes across the night sky. Now, one famous example connected to the Kuiper Belt is Halley's Comet. Although Halley's exact classification differs somewhat dynamically, it helped astronomers understand that comets follow predictable orbits rather than random appearances. Edmund Halley famously realized the comet observed in 1682 matched earlier sightings from previous centuries. He predicted its return successfully, and suddenly comets stopped seeming supernatural. They became part of the solar system, still mysterious, but understandable. Modern astronomy later extended that understanding much farther outward. As scientists discovered the Kuiper Belt during the late 20th century, the connection between icy outer populations and short-period comets became increasingly clear. One especially important group is the Jupiter family comets. These comets possess relatively short orbital periods and trajectories strongly influenced by Jupiter. Astronomers believe many began as Kuiper Belt objects scattered inward through interactions with Neptune before eventually becoming trapped into shorter orbits shaped by Jupiter. So in a sense, the giant planets act almost like gravitational relay stations passing icy objects inward through the solar system. Neptune nudges them first, then Uranus or Saturn may alter their paths further. Finally, Jupiter captures or redirects them dramatically. The outer solar system constantly exchanges material with the inner regions over immense spans of time. Now, one fascinating thing about comets is that they preserve ancient material extraordinarily well. Because many formed in the cold outer solar system early in planetary history, they contain primitive compounds dating back over 4.5 billion years. Scientists sometimes describe comets as dirty snowballs. though admittedly that phrase sounds less majestic than they deserve. Still, the description is broadly accurate. Comets contain mixtures of ice, dust, rock, and complex organic molecules preserved from the solar nebula itself. That means studying comets allows scientists to investigate conditions present during the solar system's formation. Some researchers even suspect comets may have helped deliver water and organic compounds to early Earth. The exact role remains debated because isotopic measurements vary between different comets and Earth's oceans. But at minimum, comets clearly transported enormous amounts of volatile material throughout the young solar system. Tiny icy bodies from the outer darkness may have contributed ingredients important for planetary evolution, possibly even for life itself. That is quite an impressive legacy for frozen objects drifting beyond Neptune. Now, despite their beauty, comets are temporary creatures in astronomical terms. Every time a comet approaches the Sun, it loses material. Ice sublimates into gas. Dust gets blown away. Over repeated orbits, comets gradually shrink, darken, fragment, or disintegrate entirely. Some eventually become inactive dark bodies resembling asteroids more than traditional comets. Others break apart spectacularly. One famous example was Comet Shoemaker-Levy 9. In 1994, after being torn apart by Jupiter's gravity, fragments of Shoemaker-Levy 9 slammed into the giant planet's atmosphere. The impacts produced enormous explosions larger than Earth itself. That event reminded humanity that the solar system remains dynamically active even today. Gravity continues reshaping trajectories constantly, and some of those trajectories begin in the Kuiper Belt. Now, another especially interesting object connected to both comet science and the Kuiper Belt is Arrokoth. When New Horizons visited Arrokoth in 2019, scientists discovered an extraordinarily primitive object, preserving evidence of gentle early formation processes. Arrokoth resembled two flattened lobes softly joined together, rather than violently smashed. This mattered enormously, because it suggested some Kuiper Belt objects preserve primordial structures almost unchanged since the solar system's birth. Comets originating from similar populations may therefore carry ancient untouched material from the solar nebula itself. In a way, every comet entering the inner solar system becomes a messenger from deep time, a fragment of the solar system's earliest era briefly illuminated by sunlight before disappearing outward again. And humans have watched these visitors for thousands of years without realizing where they came from. That connection between ancient skywatching and modern planetary science feels strangely satisfying. The mysterious glowing objects once feared as omens turned out to be icy survivors from beyond Neptune. Now, another important detail involves colour and chemistry. Many Kuiper Belt objects appear reddish, because radiation alters their surfaces over billions of years, producing complex organic compounds called tholins. Comets sometimes reveal similar chemistry beneath their dark crusts. Spacecraft missions studying comet nuclei discovered surprisingly dark surfaces coated in organic-rich material. Far from being bright snowballs, many comet nuclei resemble blackened chunks of ancient ice and carbon compounds. Again, the outer solar system keeps defying expectations. Even sunlight behaves differently there. At Kuiper Belt distances, solar energy becomes extremely weak. Objects remain frozen and inactive. But once one of those bodies begins moving inward, sunlight gradually awakens it. A dormant, icy world becomes active. Gas erupts from beneath the surface. Dust streams outward. Tails form. And suddenly an ancient Kuiper Belt object becomes visible across Earth's skies. That transformation is one of the most dramatic journeys in the solar system, from silent darkness beyond Neptune to blazing visibility near the Sun. Now, despite everything scientists have learned, many questions remain unanswered. Exactly how efficiently do Kuiper Belt objects become comets? How many inactive comet nuclei drift unnoticed through the solar system? How much ancient material survives repeated solar heating, and how many additional icy populations still remain undiscovered farther outward? Because the Kuiper Belt itself may only represent part of a much larger outer solar system structure, extending gradually toward the distant Oort cloud. The farther astronomers look, the more complicated the story becomes. But one thing is now clear. Comets are not random wanderers appearing mysteriously from nowhere. Many are deeply connected to the Kuiper Belt and the ancient frozen populations beyond Neptune. Every glowing comet tail crossing Earth's sky carries a piece of the outer solar system inward, a fragment of deep, cold, and ancient history temporarily illuminated by sunlight, before gravity eventually sends it drifting outward once more into the darkness where it began. At 4.8 billion kilometers from Earth, a piano-sized spacecraft moving silently through darkness changed humanity's understanding of the outer solar system forever. For decades, the worlds beyond Neptune existed mostly as blurry points of light in telescopes. Astronomers could calculate their orbits, estimate their sizes, and guess at their compositions, but the actual landscapes remained hidden behind distance and darkness. Then New Horizons arrived, and suddenly the edge of the solar system stopped being abstract. It became real. That transformation is difficult to overstate because before New Horizons, even Pluto itself remained mysterious. Humanity had known Pluto existed since 1930, yet for most of that time it appeared only as a tiny unresolved dot. No mountains, no glaciers, no skies, no visible details at all. Just a faint distant world drifting beyond Neptune. In some ways, Pluto almost felt symbolic rather than physical. It represented remoteness itself, the lonely little object sitting at the outer edge of the familiar solar system. And then a spacecraft crossed billions of kilometers of space and showed us that Pluto was not merely a frozen rock, it was an active world. Now, the story of New Horizons really began long before launch. Scientists had wanted to visit Pluto for decades, but the mission faced enormous challenges. Distance alone made the project intimidating. Even light requires more than 4 hours to travel between Earth and Pluto, when the two worlds are relatively close in their orbits. Radio communication with a spacecraft out there would involve huge delays. Real-time control becomes impossible, and reaching Pluto fast enough posed another problem. The outer solar system is astonishingly large. Traditional spacecraft speeds would require decades upon decades to arrive. Engineers needed New Horizons to travel extremely quickly, faster than any previous spacecraft launched from Earth. Eventually, on January 19, 2006, NASA launched New Horizons aboard an Atlas V rocket. It departed Earth at roughly 58,000 kilometers per hour. For a moment, humanity had built the fastest object ever launched from its home planet. Even so, the trip to Pluto still required nearly 9.5 years. That alone says something profound about the scale of the solar system. The fastest spacecraft humans had ever created still needed almost a decade to reach Pluto, and Pluto itself was not even the true edge of the solar system. Along the way, New Horizons crossed the orbit of Jupiter, using the giant planet's gravity to gain additional speed through a gravitational assist maneuver. Jupiter itself provided an early preview of the mission's scientific potential. New Horizons captured detailed images of volcanic eruptions on Io and observed complex atmospheric behavior on Jupiter itself. But the real destination still lay far ahead in deep darkness. Meanwhile, back on Earth, Pluto remained mysterious. Scientists debated its atmosphere, surface composition, geology, and internal structure endlessly because direct observations were so limited. Some imagined a heavily cratered dead world. Others suspected more complexity. No one fully anticipated what New Horizons would reveal. Then finally, in July 2015, the spacecraft arrived, and Pluto changed completely. The first close images stunned scientists almost immediately. Instead of a heavily battered ancient surface everywhere, Pluto displayed huge smooth regions, almost entirely lacking impact craters. That meant geological activity. Something on Pluto had resurfaced parts of the world relatively recently. The most famous feature became the enormous heart-shaped region later named Tombor Regio, after Clyde Tombaugh. Again, the universe occasionally displays suspiciously cinematic timing. After decades of treating Pluto as the lonely forgotten world at the edge of the solar system, humanity finally arrives and discovers a giant heart on its surface. Within Tombor Regio lay Sputnik Planitia, an immense nitrogen ice basin unlike anything previously seen in the outer solar system. This region looked smooth and strangely cellular, almost like giant cracked polygons stretching across the landscape. Scientists eventually concluded that ice there slowly convects over time. Imagine an enormous frozen lava lamp operating over geological timescales. That is essentially what Pluto was doing. The nitrogen ice warmed slightly from below, rose upward slowly, cooled, and sank again. Even in deep, cold billions of kilometers from the sun, Pluto remained active. And then came the mountains. Towering blocks of water ice rose several kilometers high across Pluto's surface. At Pluto's temperatures, water ice behaves like solid rock because conditions are so cold. Meanwhile, softer volatile ices like nitrogen and methane flow more easily. This creates landscapes unlike anything on Earth. Frozen nitrogen glaciers move slowly around mountains made of water ice beneath a dim, distant sun. It sounds invented, yet it exists. New Horizons also revealed atmospheric haze layers extending high above Pluto's surface. Thin blue atmospheric bands stacked one above another through the sky. The atmosphere itself changes seasonally as Pluto moves along its elongated orbit. Surface ices vaporize under weak sunlight, and later freeze again as conditions shift. Entire atmospheric cycles happen there, slowly, quietly, but unmistakably. And perhaps most importantly, Pluto no longer looked isolated. It looked like one member of a much larger population of complex outer solar system worlds. That realization transformed the entire scientific meaning of the Kuiper Belt. Before New Horizons, many people still imagine Kuiper Belt objects as mostly inert, icy leftovers. But Pluto demonstrated that even small distant worlds could possess geology, atmospheres, and active surface processes. The outer solar system suddenly felt much more alive. Now, one especially emotional moment during the mission involved the first high-resolution images arriving on Earth. Because of the communication delay and limited transmission speed, New Horizons could not send everything immediately. Data trickled back slowly over many months. At Pluto's distance, radio signals become extremely weak. The spacecraft's transmitter operated with less power than a household light bulb, yet somehow those faint signals crossed billions of kilometers successfully. That fact alone feels astonishing. Humanity launched a machine across the solar system and maintained communication with it using radio waves weaker than ordinary home electronics. And somehow, it worked. Now, after Pluto, New Horizons did something equally remarkable. It kept going. Most planetary missions end after their primary flyby targets, but New Horizons still possessed enough fuel and operational capability to continue deeper into the Kuiper Belt itself. Scientists searched carefully for additional targets within reachable distance. Eventually they selected a tiny object initially nicknamed Ultima Thule, and later officially named Arrokoth. Arrokoth became humanity's first close encounter with a primordial Kuiper Belt object. And once again, reality surprised everyone. Instead of a shattered, chaotic body, Arrokoth appeared delicate and strangely smooth. Two flattened lobes gently connected together, resembling a snowman assembled in slow motion. Scientists believe Arrokoth formed through an extremely gentle merger early in solar system history. Not a catastrophic collision, more like two drifting icy bodies softly touching and sticking together. That mattered enormously, because it suggested some Kuiper Belt objects preserve incredibly ancient primordial structures. Arrokoth may resemble the original building blocks from which planets formed, a surviving fossil from the solar system's construction era, and, because Arrokoth remained relatively undisturbed for billions of years, it preserved clues about early planetary formation processes remarkably well. Its surface appeared dark reddish in colour due to radiation altering organic compounds over immense timescales, and importantly, Arrokoth looked primitive, untouched, like something preserved in a freezer since the solar system's earliest days. New Horizons therefore accomplished something extraordinary scientifically. It transformed the Kuiper Belt from a theoretical population into a real explored region filled with actual landscapes and complex worlds. The outer solar system stopped feeling abstract. Now, another fascinating discovery involved the relative scarcity of impact craters on some Kuiper Belt surfaces. This hinted that collisions in certain outer regions may have occurred less frequently or differently than expected. The Kuiper Belt appeared dynamically quieter in some ways than earlier models predicted. Again and again, New Horizons forced scientists to rethink assumptions. That became one of the mission's defining themes. Every major flyby revealed unexpected complexity, and this seems to happen repeatedly in planetary exploration. Whenever humans finally visit distant worlds directly, those places turn out stranger and richer than telescope observations alone suggested. Mars had ancient river valleys. Titan possessed methane lakes. Europa may conceal a global ocean. Pluto had nitrogen glaciers and atmospheric haze. Reality consistently exceeds imagination. Now, perhaps the most emotionally powerful thing about New Horizons is how isolated the spacecraft became. As it travelled outward, Earth gradually faded behind it. Sunlight weakened. Communication delays increased. The spacecraft entered regions no human-made object had previously explored in detail, and yet it continued operating faithfully in temperatures near absolute zero, crossing billions of kilometers through darkness with astonishing precision. There is something deeply human about that mission. Tiny creatures from one small planet launching a machine across the solar system simply because they wanted to know what existed out there. Curiosity carried New Horizons farther than any symbolic national boundary or practical necessity. We went because we wanted to see. And what we saw changed the outer solar system forever. Pluto became a world rather than a point of light. Arrokoth became evidence of primordial planetary formation. The Kuiper Belt became a place rather than merely a hypothesis. And perhaps most importantly, New Horizons revealed that even at the edge of sunlight, in regions once imagined as frozen, empty wastelands, the solar system still contained complexity, activity, and ancient stories waiting silently in the darkness beyond Neptune. Deep in the outer darkness beyond Neptune, certain objects move in ways that continue bothering astronomers. Not dramatically. Not in the sense of alarms or panic or sudden impossible discoveries that overturn physics overnight. Real scientific mysteries are usually quieter than that, more subtle. A collection of small inconsistencies slowly building over time until researchers begin noticing that something about the data refuses to behave normally. And in the distant regions beyond the Kuiper Belt, several icy worlds appear to follow strangely organised orbital patterns. That alone would already be interesting. But the possible explanation became one of the most fascinating modern mysteries in astronomy. What if something massive still lurks far beyond the known planets? Now, it is important immediately to separate this idea from the older concept of Planet X because people often mix them together. For much of the 20th century, astronomers searched for hypothetical hidden planets, partly because they believed irregularities in Neptune's orbit required another massive object farther outward. Eventually, those orbital discrepancies turned out mostly to result from inaccurate measurements, rather than an unseen giant world. That earlier search accidentally led to the discovery of Pluto, but Pluto itself proved far too small to explain the supposed gravitational effects. So for decades, the idea of another major planet beyond Neptune gradually faded from serious astronomy. Then the Kuiper Belt was discovered, and suddenly the outer solar system became complicated again. Thousands of icy bodies appeared beyond Neptune. Some followed elongated or tilted trajectories. Others occupied stable resonances controlled by Neptune's gravity. Most of these orbits made sense within existing models involving planetary migration and gravitational scattering, but not all of them. A few objects behaved oddly enough to raise new questions. One of the most important examples is Sedna. Sedna follows a bizarre elongated orbit carrying it incredibly far from the Sun. At closest approach, it remains roughly 76 astronomical units away. At its farthest, it may drift beyond 900 astronomical units. And here is the key problem. Sedna never comes close enough to Neptune for Neptune alone to explain its trajectory comfortably. Something else appears to have influenced it. At first, astronomers considered passing stars as a likely explanation. The Sun probably formed within a dense stellar nursery billions of years ago, and close encounters between young stars could potentially disturb distant icy bodies gravitationally. That remains plausible. But then additional strange objects appeared, and some of them showed peculiar orbital similarities. This is where the modern Planet 9 hypothesis emerged. Around the mid-2000s, astronomers including Konstantin Batyan and Michael E. Brown noticed that several extremely distant objects shared unusual orbital alignments. Their elongated orbits clustered in roughly similar directions. Statistically, that clustering looks strange. Imagine tossing several pencils randomly onto a floor and discovering they all point nearly the same way. One or two might happen by chance. But enough similar alignments begin suggesting some organizing influence. In this case, that possible influence was gravity. Specifically, gravity from an unseen massive planet far beyond Neptune. Now, if Planet 9 exists, scientists do not imagine a giant gas world like Jupiter. Instead, current models suggest something perhaps 5 to 10 times Earth's mass. Large enough to dominate distant gravitational environments, but still much smaller than the giant planets closer inward, and the proposed orbit would be enormous. Some estimates place Planet 9 hundreds of astronomical units from the Sun, perhaps following a highly elongated path requiring thousands or even tens of thousands of years to complete once. At those distances, sunlight becomes incredibly weak. The Sun itself would no longer dominate the sky emotionally. It would appear more like an intensely bright star. Temperatures there would be extraordinary. Permanent deep cold, vast darkness, a world drifting slowly through the outer edge of the Sun's influence, and importantly, finding such a planet would be extremely difficult. People sometimes ask why astronomers cannot simply point a telescope outward and locate it immediately, but the sky is a sea, and objects that distant appear incredibly faint. Planet 9, if real, would reflect only tiny amounts of sunlight while moving very slowly against background stars. Detecting it could require years of careful observation. In fact, several major telescopic surveys continue searching systematically even now. Still no confirmed detection exists. That is important to emphasize repeatedly. Planet 9 remains hypothetical. Some astronomers consider the evidence compelling. Others remain skeptical, and the skepticism is reasonable because astronomy has experienced false alarms before. Sometimes patterns emerge from incomplete data simply because humans naturally search for order. This issue becomes especially important in the outer solar system, because observational bias can distort discoveries significantly. Astronomers do not survey every region of sky equally. Certain areas receive more attention. Some objects are easier to detect than others. As a result, clustering patterns might occasionally appear stronger than they truly are. In other words, the evidence remains suggestive rather than conclusive. Still, several additional observations continue fueling interest in the hypothesis. Certain distant objects possess unexpectedly tilted orbits. Some travel nearly perpendicular to the solar system's main plane. Others occupy regions difficult to explain through known planetary interactions alone. A sufficiently massive distant planet could potentially account for many of these anomalies simultaneously. Now, whether Planet 9 exists or not, the discussion itself reveals something fascinating about the solar system. Humanity still does not fully understand its outer structure. Even now, after centuries of astronomy, after spacecraft missions to multiple planets, after mapping thousands of exoplanets around other stars. Our own solar system still contains regions so remote and dark that major objects might remain undiscovered. That realization feels strangely humbling. Now, interestingly, the search for hidden planets beyond Neptune has happened before in different forms. During the late 19th and early 20th centuries, astronomers suspected unseen worlds because of apparent irregularities in planetary motions. Those efforts eventually contributed to Pluto's discovery, but Pluto turned out too small to explain the original calculations. Then later, improved measurements largely resolved the orbital discrepancies entirely, so astronomers became cautious about invoking invisible planets too quickly, and yet here we are again. The outer solar system refuses to behave neatly. Now, one especially fascinating aspect of the Planet 9 idea involves formation history, because if such a planet exists, how did it end up so far away? Several possibilities exist. Perhaps Planet 9 formed closer to the Sun, alongside the other giant planets, before gravitational interactions ejected it outward into a distant elongated orbit. That scenario fits reasonably well with models of early planetary migration and instability. The young solar system appears to have been remarkably chaotic. Giant planets moved, objects scattered everywhere, entire populations of icy bodies were disrupted. So a large planet getting thrown outward is not impossible. Another possibility is even stranger. Maybe the Sun captured Planet 9 from another star long ago while still inside its birth cluster. Young stars forming together can pass relatively close to one another compared to their current separations. Under certain conditions, gravitational interactions might allow one star to steal planets from another. Imagine losing an entire planet to a neighbouring star during the solar system's childhood. The universe can be surprisingly rude sometimes. Of course, these ideas remain speculative because Planet 9 itself remains unconfirmed. Still, the possibility opens fascinating questions about how planetary systems form and evolve. Now, beyond the Planet 9 debate, the outer solar system contains additional mysteries suggesting its structure may extend much farther and more gradually than older models assumed. Objects like Sedna occupy what astronomers sometimes call detached orbits. They appear partially disconnected from Neptune's direct influence. Farther outward may lie the inner Oort cloud, a vast spherical population of icy bodies potentially extending tens of thousands of astronomical units from the Sun. If the Oort cloud exists as predicted, then the Kuiper Belt represents only the beginning of the Sun's true outer frontier. The solar system would not end near Pluto at all. It would continue vastly farther into darkness. Now, emotionally speaking, the possibility of unseen worlds beyond Neptune touches something ancient in human curiosity. People have always wondered what lies beyond the known horizon, beyond the next mountain, beyond the ocean, beyond the final mapped territory. Astronomy simply moved that instinct outward into space, and again, the universe responded by revealing larger structures than expected. Humans once thought the planets ended with Saturn because Saturn was the outermost visible planet. Then Uranus appeared, then Neptune, then Pluto, then the Kuiper Belt, then detached objects like Sedna. Each new discovery expanded the map, so perhaps it should not surprise us that astronomers continue searching for additional worlds hidden in the dark beyond the known Kuiper Belt. And if Planet 9 eventually turns out not to exist, the mystery itself still matters, because it demonstrates how incomplete our understanding remains. The outer solar system is not fully mapped territory. It is an active frontier of discovery. Even now, distant icy objects continue appearing in astronomical surveys. Strange trajectories continue challenging existing models. New telescopes continue scanning enormous regions of sky, looking for faint motion among the stars. Somewhere out there, beyond Neptune and beyond the scattered icy worlds of the Kuiper Belt, gravity still leaves clues in the darkness. And whether those clues point toward a hidden planet, ancient stellar encounters, or something astronomers have not imagined yet, the edge of the solar system remains one of the few places in modern science where genuinely large unknowns still drift quietly through the cold. At immense distances beyond Neptune, the solar system slowly begins fading into darkness. Not ending suddenly, not stopping at a clean border, just gradually becoming quieter, colder, and harder to understand. This is the strange reality humanity eventually discovered while exploring the Kuiper Belt. What once looked like empty space beyond Pluto turned out to be an enormous frontier filled with frozen worlds, ancient debris, chaotic orbits, and mysteries stretching outward farther than earlier generations ever imagined. And even now, after decades of study, the outer solar system still feels unfinished somehow, partly mapped, partly hidden. A region where known objects drift through deep cold, while unseen ones may still wait farther outward beyond the limits of current observation. Now, one reason the Kuiper Belt feels emotionally different from the rest of the solar system is because sunlight itself changes there. On Earth, sunlight dominates everything. It fills skies, shapes weather, powers ecosystems, and controls daily life so completely that most of us rarely think about how overwhelming the sun actually is. Closer planets feel that dominance too. Even at Mars, sunlight still looks familiar enough that humans can imagine standing beneath it without too much difficulty. But farther outward, beyond the giant planets, something shifts. The sun gradually shrinks in the sky. At Pluto's distance, sunlight is already about 1,600 times weaker than on Earth. Still bright enough to cast shadows, still unmistakably sunlight, but thinner somehow, more distant emotionally. And beyond Pluto, the effect grows stronger. Out there, daylight would resemble permanent twilight compared to Earth. The sun would no longer feel like a blazing ruler dominating the heavens. Instead, it would appear more like an extremely bright star suspended in endless blackness. That visual transformation matters psychologically because it changes how humans imagine the solar system itself. The inner planets feel connected to the sun directly. The Kuiper Belt feels like the beginning of separation, a transition zone between the familiar planetary system and the vast outer darkness beyond. Now, despite the enormous distances involved, the Kuiper Belt is not dead. That is one of the most surprising lessons modern astronomy revealed. For a long time, scientists assumed distant icy worlds would be geologically inactive relics frozen unchanged forever. Then New Horizons arrived at Pluto in 2015, and Pluto turned out to be astonishingly alive in a geological sense. Nitrogen glaciers moved slowly across the surface. Atmospheric hazes layered the sky. Enormous plains showed evidence of resurfacing. Mountains of water ice towered above frozen valleys. Even at the edge of sunlight, planetary processes continued. That discovery changed the emotional feeling of the outer solar system completely. Suddenly, these distant objects stopped being abstract points of light. They became places, cold places, silent places, but real worlds nonetheless. And Pluto is only one among many. The Kuiper Belt contains huge populations of icy bodies, ranging from tiny fragments to large dwarf planets like Eris, Makemake, and Haumea. Some possess moons, some rotate chaotically, some may contain hidden subsurface oceans insulated beneath frozen crusts, and countless additional objects almost certainly remain undiscovered. The farther astronomers search, the more the solar system expands. Now, one especially remarkable thing about the Kuiper Belt is how ancient it is. Many of these frozen objects formed over 4.5 billion years ago during the earlier stages of planetary formation. Unlike Earth, where tectonic activity, erosion, and weather constantly reshape the surface, many Kuiper Belt objects preserve extremely old material relatively unchanged. They are cosmic fossils, time capsules from the solar system's youth, and because they survived in deep cold for billions of years, they preserve evidence about how planets formed and how the giant planets migrated long ago. The Kuiper Belt is not merely debris, it is history. Ancient history orbiting silently beyond Neptune. Now, emotionally speaking, there is something deeply strange about imagining these distant worlds continuing their slow journeys while human civilization occupies only the briefest instant of their existence. Pluto requires 248 Earth years to orbit the Sun once. Some detached objects take thousands. Sedna needs roughly 11,000 years for a single orbit. Human history barely registers against such timescales. Entire civilizations rise and disappear during tiny fractions of these orbital periods, and meanwhile the objects themselves simply continue drifting through darkness patiently. Orbit after orbit. Century after century. The outer solar system moves slowly, very slowly. Now, another reason the Kuiper Belt matters so much is because it changed humanity's understanding of what the solar system actually is. For generations, people imagined a relatively tidy arrangement of planets ending with Pluto. Then astronomers discovered the Kuiper Belt, then the scattered disk, then detached objects with bizarre trajectories, then possible evidence for unseen massive worlds farther outward. The solar system stopped looking simple, and perhaps more importantly, it stopped looking finished. Even today, astronomers continue discovering new distant objects every year. Some follow unexpected orbits, some challenge existing theories, some hint at gravitational influences not fully understood. And somewhere beyond the known Kuiper Belt may lie the hypothetical Oort cloud, a gigantic spherical population of icy bodies extending perhaps tens of thousands of astronomical units outward. If the Oort cloud exists as predicted, then the Sun's gravitational domain reaches astonishingly far into interstellar space. The Kuiper Belt would represent only the inner edge of a much larger outer frontier. Now, perhaps the most fascinating aspect of the Kuiper Belt is how incomplete our understanding remains. People sometimes assume modern astronomy has mapped the solar system fully, not even close. The outer regions remain extraordinarily difficult to study because objects there are tiny, dark and distant. Many reflect very little sunlight. Some move so slowly against the stars that detecting them requires years of careful observation. And because current surveys can only cover limited regions effectively, there may still be large undiscovered objects hiding in the darkness. Possibly even additional dwarf planets, maybe more. The solar system continues holding secrets. That realization feels refreshing somehow. In an age where humans map entire continents with satellites and carry vast libraries inside small electronic devices, it is comforting to remember there are still enormous unexplored regions orbiting our own star. The frontier never fully disappeared, it merely moved farther away. Now, one especially beautiful moment in modern planetary science came when New Horizons continued beyond Pluto and visited Arrokoth. Arrokoth turned out to be remarkably primitive and delicate in structure. Two flattened, icy lobes gently joined together, preserving evidence of slow, peaceful formation processes from the earliest solar nebula. Not all of the solar system formed through violent collisions. Some worlds assemble quietly, and Arrokoth preserved that ancient calm for billions of years in deep cold beyond Neptune. There is something fitting about that. The Kuiper Belt itself feels quiet compared to the rest of the solar system. Not empty, not lifeless, just quiet. The giant storms of Jupiter do not rage there. The volcanic eruptions of inner moons do not dominate the landscape. Even sunlight softens into something dimmer and more distant. and yet beneath that quietness lies extraordinary importance. The Kuiper Belt preserves clues about planetary migration, comet origins, early chemistry, and the formation of the solar system itself. It transformed Pluto from an isolated oddity into part of an enormous hidden population. It revealed that the solar system extends much farther and more gradually than once imagined, and it reminded humanity that even our own cosmic neighbourhood remains only partially explored. Now, as strange as it sounds, the Kuiper Belt also changes how we think about home. Earth feels central to us because we live here. The inner planets feel familiar because sunlight remains strong and immediate there. But the Kuiper Belt exists at the threshold where the sun's warmth begins losing its dominance. It marks the beginning of the outer dark, a frontier between the bright planetary system humans know and the immense colder regions beyond. And somewhere out there tonight, while people sleep beneath warm skies on Earth, countless frozen worlds continue circling slowly through deep space under faint sunlight that left the sun hours or even days earlier. Silent objects older than mountains, older than oceans, older than life itself, still orbiting patiently at the quiet edge of sunlight, while the solar system stretches farther outward into darkness than humanity once ever believed possible.